2 of my Lean4 live proving series, I guess. So I'm working on a prime sieve, and actually have a little bit of a demonstration of what that is this time. It's not quite ready to go, but so this is the sieve of Eratosthenes. You have all the numbers from 2 all the way up to whatever, however high you want to go, and when you click it, I mean, it goes by really fast. So, but what it does is just for a split second there, you can see it's actually I could slow it down, I guess. You just sleep a little bit longer, and yeah. So, oh, even that's too fast. Fast. Sorry, I should have done this a second ago, but be a long stream anyway. Sleep 0. So yeah. Wow. Okay. Well, never mind then. I'm working on the animation. I'm gonna, you know, I'm planning to have a real animation for the video that I'm making for Summer of Math Exposition. But anyway, the idea is that, you know, you mark off every multiple of 2, and then you say, okay, well, 3 is the next number, and then you can actually jump all the way up to since there's no primes less than it, you know, the next compound number must be 3 squared, and so or the next everything that you haven't marked off, right? So 2 marks off 4, 6, and 8, and all these other numbers, and then 3, you know, 3 squared is 9. So the next everything between 3 and 9 is going to be prime. Anyway, you keep doing that. You mark off all the multiples of 3. 6 would have already been gone, so then 9 and basically this row, I guess. No. Anyway, but then there's a trick you can do where you could just say, well, you know, nothing in this row is ever going to be prime, and nothing in this row is ever going to be prime except 2. 3 is the only one in this row. And of course, that only matters if it's, you know, if the width of the table is arranged so that they form a column. But anyway, you can strip out the rows. You can strip out the even numbers to begin with, and then you can move your little cursor around faster. And yeah, I'm just rambling here at this point. Anyway, that's a prime sieve. And then there's this notion of a wheel that strips out even more, but I haven't implemented the main part of it, so it thinks 25 is prime and so on. It's not a bug. I just haven't done I haven't done the work to make this do the right thing. So yeah, I'll leave that off the screen. And you can keep adding to that. So what this prime sieve does, I wouldn't say it's I mean, it's the one I'm working on. I didn't come up with the idea, but it just uses a series of arithmetic expression or sequences. So we start out with, you know, the formula, you know, constant term is G, just because Decker wants to be called G. I usually call it K. And so G plus 1x is this straight line, just the identity function. We start with 2 because we don't want 1 to be prime. So 2 is the first number in the sequence, and therefore it's, okay, that's prime. And then we partition this, and we partition this into all the things that are, you know, 0 mod 2 and 1 mod 2, so all the evens and the odds. And then of course we strip out the evens, so this gives us the odd numbers. And so now we're at you know, 3 plus 2x, and you get this line. So what's happening? It's a little hard to see in Decker, but you know, this number is like basically doubling up here because I've multiplied everything by 2, and then you know, the line is moving to the left, right? It's tilting up to the left. Same thing with 3. And now we have 2 lines, right? Because we have all the multiples of 5 and the multiples of 7, and you can see that like all the numbers that, not quite this way, but like the numbers that would be on this, that were on this line and in between here, those points kind of moved over to the left, and now they made a separate line. And then we're going to, you know, partition again, and we multiply this by, so now we've multiplied 2 and 3 together. We're going to multiply by 5. We're going to get 30, and then we're going to do every you know, that's gonna partition those two lines into a bunch of lines that are generating or sequences that are generating numbers that are either multiples of 5 or whatever. So we strip out the ones that were multiples of 5. There was a 25 in here, for example, and I think maybe 35 or something like that. I don't know. And I guess each of the originals, you have 5. You make 5 copies of it, and then there'll be 2 of them of those copies that we strip out. We strip out one line to make a. It's a little hard to see, but basically you're stacking up parallel lines, and so back when I get to W7, W is for wheel. That's just the term they use for this. You can't even see the lines here because Decker draws them in white, but basically there's I think 9. Yeah, so there's 9. No, sorry. How would I know? However long this list is. So 1, 2, 3, 4, 5, 6, 7, 8. Is that right? 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Anyway, so I guess there's 8 of them. Yeah, that's right. There's 8 of them. Sorry, there's 8 of them in this one. It doesn't look like it looks like there's like 3 of them, but there's actually 8 different things here. So there's a line that's 7 plus 30x, 11 plus 30x, 13, 9, 17, and so and then when you get past that, it explodes, right? There's just way too many because you're multiplying by a prime each time. So it's 2 times 3 times 5 times 7 times 11 times 13 and so on, and you get all these terms. And so it's not a very it's not a terribly efficient system for finding primes, in the sense that you have to track all of these arithmetic sequences. But on the other hand, like once you filter these numbers out, the very first term, so in this case 11, oh sorry 7, they're not sorted here. In this case the 7, every one of these terms that you see that are less than 7 squared, so 49, they're all prime. So you're generating, you're generating the next prime, and whatever that number is squared, like everything between that number and n or p and p squared, everything between that is guaranteed to be prime. And so you kind of are generating like quite a bit of these every time, quite a few of these every time. So that's the idea, and also because you're multiplying the number of lines each time, and they're kind of accelerating. The line is getting steeper and steeper. What's going to happen is that the delta term, the slope, grows extremely fast because it's like similar to a factorial. It's a primorial. It grows faster than a factorial. Sum of the first n primes is at every step, and so the slope is very big, and so the first couple terms are going to be very, very large. You're going to get very big numbers, and then you're going to have one for every. You're going to have many of those rows, and like at each step, you're stripping out. You're increasing the density of primes in each. You wind up, very quickly generating some very, very large numbers that are likely to be prime, or at least higher. Where the density of primes is higher, so that you're more likely to find one than just by randomly picking a 12-digit number. I mean a 100-digit number or something like that. Anyway, that's me. That's enough rambling. Let's get into Lean. So the way I've structured this, updated from last time, I think the major idea that I had, I'll just kind of recap it. So I wrote my implementation. It's basically this, which doesn't look like very much, but it's using a data structure called a ASEQ for arithmetic sequence. We have a K and a D, so it's just literally this binomial or whatever. You've got delta, so the step size times n, the input number plus K, or what you're seeing here. So it's just a line, the equation for a line, except you only give it discrete input, so it's called a sequence. If you sum them up, that's called a series. The infinite sum of that sequence is called a series. Anyway, so I guess I've already done this part. So anyway, what I've made so far, and I kind of covered this a little bit last time, is I had this equation where I use this data structure, and I make it so that you can actually you can evaluate the nth term of that sequence, and then you can compose two sequences, and this is how we partition. We take the first line, you know, um, you know, so 2 plus 1n, right? So in this case, 2 plus 1x, right? That sequence becomes, we start with the identity sequence, which is 0 plus 1n, right? That's the identity, and then if you want the ones greater than 1, I guess, then you would say you would add greater than or equal to 2, then you would add 2 to that. So it would be 2 times 1n. And then to filter that, then you compose that. So you feed in, you break the inputs into, again, you break the inputs into these. So you make it into 2 lines. So it's got a 5 and a 7 or whatever, or in this case, the term, what am I trying to say? You break the evens are 0 plus 2n and the odds are 1 plus 2n. That's how you generate them. So you're partitioning at each step, and then every time you partition it into 2 pieces, 3 pieces, 5 pieces, 7 pieces, 11 pieces, 13, and so on. And so you just keep multiplying that number, and then you strip out the ones that happen to be multiples of. Like when you get to 5, there'll be a term, or there'll be a row that says like 5 plus would have been 5 plus 30x, and then it would be we stripped out, and then we also would have stripped out 25 plus 30x. So that because 30 now contains the 5, right? So we've already stripped out that prime. Anyway, that's the idea. This works. You can see it generates primes like almost immediately, and it's ridiculously large. But the idea was to kind of do like some just some. I guess maybe somebody could do some theory or proving about the sieve itself. A couple years ago, some people did some work on the prime number theorem and got not the twin primes conjecture, saying that the conjecture is that there's always 2 primes, no matter how high you go. There's always 2 primes that are higher than it, that are separated by 2 numbers. So it's p and p plus 2, and they don't know how to prove that yet. Nobody knows how to prove that yet, but they've gotten it down to p and p plus 264. There's always at least a number. There's always at least another prime that's 264 or fewer away, according to the last proofs that were a couple years ago. And I thought it would be interesting at some point maybe to work on this. And the original idea for this was from a friend of mine who wants to do that kind of thing. Anyway, but I always said if you're going to work on this stuff, if you're going to do recreational mathematics seriously, and you want like anything you find to be taken serious by mathematicians, and you don't want to fool yourself, then maybe you should formalize it in a formal theorem proving system. And I don't know if that's good advice or not, because I don't know how hard it is to do this. So I've been trying. I've been trying to like just take the basic idea for this sieve and implement it. Like I said, that works. This is all just like basic functional stuff, because all I did was I made a partition function, and it doesn't prove anything, right? Like all I did is I did the math. I see that it works, but I haven't proven that it works. So I can't. Obviously, like everything that I'm going to discover about primes, has already been discovered for millions of years. But like in theory, or hundreds of years, I couldn't be. What am I trying to say? I I guess there was a time when you could when amateurs could have submitted something to the equivalent of a journal and you know gotten credit for their ideas or whatever. But that time is long gone. Like the people who are professional mathematicians, I think, uh, like they know what they're doing and they're doing everything. They've swept up all the easy questions. I think you have to come up with a new question if you want to do something easy, right? You have to open up a whole new area of mathematics, and probably it's not going to be terribly deep. Anyway, I'm rambling here. My point is that like as anybody who is like currently working like outside of academia is going to have several problems because of that. One, they're not going to be, they don't have advisors to bounce ideas. Maybe you can get help online or whatever, but you don't have advisors. You don't have the mentorship, the professorship and PhDs. You don't have that mentoring system in place. And then two, you don't have the attention of people. So if you find something you can't, and you publish it, well, you're likely to be ignored, right? You don't have the name recognition or the way to get people's attention. It's not entirely true. You put stuff up on archive or whatever, but when it comes to the things that people tend to try and work on, like so many people will jump in and start working on the Collatz conjecture or like these ridiculously hard problems that have been open for hundreds of years or decades or whatever, and they just get laughed at, kind of. And it's for as I said, part of it because they're outside, and part of it is because people, it's very easy to fool yourself, and so you need somebody to review peer review. You need somebody to point out your mistakes, and if you don't have that, because you don't have somebody who's like already invested in you and willing to spend the time to like read your work, then I think it would benefit you to have like an automated system to do that, and that's what Lean provides. So I personally don't have any like interesting mathematical ideas that I want to explore. So I just, but I wanted to explore the notion itself. So I'm just taking just basic idea of a prime sieve and trying to implement it. Anyway, all right. So since the last time I came up with this idea called a rake, and a rake is as I said, like you've got like here you've got 1, 2, 3, 4. I think we said 8, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. We have 8 lines that are superimposed on each other. And I can't zoom into this, but if I could, there would be 8 dots on each row here. And that's representing a span of ooh, what happened there? Oh, I see, because I clicked on it. The click handler is what updates this thing. So when I clicked on this, it fired a click event. But right, so when you put the first 3 primes in, you get 30 lines because you multiply 2 times 3 times 5, but you've stripped out all but 8 of them. So that's what I'm saying. Like you've stripped out, I guess, 22 out of 30 lines are stripped out. So you've increased the density of primes by that amount by stripping out all the coprimes, right? The coprimes of these 3 primes. And by this one, you have like way more. You've stripped out a bunch more, but as you can see, it's quite big. I don't know. I don't actually know what the number is. Anyway, but there's like some diminishing returns to this approach, and so nobody really does this. But on the other hand, you can see your again. I'm not making any assertions. My advice is to always prove any statement you're going to make if you're like any kind of amateur working in mathematics. And so, but it might be interesting to explore the idea that as these I'm calling this a rake because you can imagine a line through the bottom one and the bottom one. It's like dragging a rake down this line with all these little tongs, and the number of tongs keeps growing, as you multiply by all these steps. and like, because at each step, you're starting with, this is my friend's idea, right? That you're starting with, 5 and you started with evens and odds. You broke that into, 5 and 3, 5, and 7. You stripped out all the threes. Now you got multiples of 5, multiples of 7, and like, not multiples, but well, they're on this line that, they're 2 apart is what is the key idea that I'm trying to get at. And every time you rapidly increase the number of things that are 2 apart, number of lines that are 2 apart, right? Because you double the number of lines, or not double, you multiply by 5, right? So if you have things that are 2 apart here, and then you do times 5, so where there's 2 here, now we have 8, and they're in pairs, right? So one of these was we lost a pair here. So 5, we had 5 and 7, and then the 5 went away. But so we lost, we replaced one pair with a singleton 7, but the others are 11 and 13, 17 and 19, 23 and 29, and then I guess the 5 got replaced with a 31, I believe. No, sorry, 23 and I don't know what I'm talking about. 23 and 25, sorry, that's what I was going to say. 23 and 25 would have been another pair. So we striked out 2 pairs. We striked out the 5 from the 5 and 7, and we striked out the 25 from the 23 and 25. I'm rambling. Not important. Anyway, point is, there's something to explore there, and maybe you could make some kind of statements there. Maybe, someday somebody, following this line of logic, could try and prove something that brought that gap down from 264 to 263. I don't know. I think that is beyond my skills, but I have the ability to state the problem anyway. Anyway, so let's get in here. So that's what a rake is. The rake is the collection of the lines that all have the same, or the sequences that all have the same, whatever. And I've made a structure corresponding to that. So you have some number d, and that is the slope, the delta, so the 30 here. And you have the sequences, so that would be these sequences. The sequence 7 plus 30, 7 plus 30n, 11 plus 30n, 13, all these 8 sequences would be in that list. And then you have this, which is not a data field. You can see the type is prop, right? So it's a type. Prop is a type, a proposition. It is associated with this structure, and for every instance of this structure, you need to have this value. And this value, a value of this type, is basically a proof that this list is sorted. That the list of sequences is sorted, which requires a proof that you can sort these structures, right? So all that exists. And then there's another proof that the length of the sequences is greater than 0. Right, so you always have something in there, so it's not the empty set. So, and so then this rake concept, in some sense, models this set of numbers, right? Like it doesn't actually calculate all these. It's showing this, right? It's just the coefficients for it has one number or one number that's repeated many times unnecessarily. It is the slope, and then or the delta, and then it has the coefficients of the first term. And whichever one is the lowest one of these, obviously, the lowest member of this set of numbers is going to be one of these one of these constant coefficients here. So that when you say, 30 times 0 plus g, well, it's going to be one of the g's. It's going to be one of the constants. I call it k over here. Decker wants this to be called g for group for scatterplot, or scatterplot library one. Anyway, right. So we're saying it's not the empty set, and then other ones that are there, it's sorted. So then that what follows from that is that the minimum item from this, if you want to select an item from this the set that this models, we just take sequences 0 and take the first item of that. And so that would give you the smallest number, which in this case is 7, which is the next prime. And then you keep applying the same thing, and that smallest number is always going to be the next prime, which you then eliminate, and then you move on to the next line and so on. Okay, so now we start with the identity rake, which is this. And so, okay, and I have to, so a D sequence is exactly the same as an A sequence, except the type itself now contains the number D. And so it's all the arithmetic sequences where the delta on the sequence is this thing. And so you can create like a type that encompasses that idea. They're all the same. And then from that we lift it. There is such a thing. Here's an example. For any D, there's always going to be a line that has that slope, right? And then this lets you run it like a function. I'm not sure what S is here. S is a natural number, and then S is the sequence, right? Okay. And then, anyway, but so you can actually just treat this as if it were a function. This is a coerced function. And then now, because they're in the you want to have a list of these things that all share. You want to have a list. Given D, you want a list of all of arithmetic sequences that share the same D, and so this type checks that. And then you want to be able to sort that, and because of this proposition here, so to get the first minimum item. And so that's you have to prove that it's less than. You have to prove that, or you have to prove that there is a less than relationship on these things, and you could do that by looking at the natural numbers, or you could just define it based on the constants. And then you can say that that ordering is total, which just means that exactly for x and y, either one is less than the other, or the other one is less than the other. So there's no. I guess there would be equal, but like if you're ordering them, they're not going to be matched up or whatever. I guess that's what that's saying. Oh no, because they are equal. But basically what it's saying is that, like, what does it mean to order points on the complex plane, right? You have to order them like you have to choose one of the fields to be more important or whatever. Or you could choose to order them by distance, but then like everything in one circle is around the point is the same distance from the origin or whatever. So like you have to choose how to define an order on that. And then if you have the case where they are all on one circle and those are all like equally sorted, then that's not a total ordering. But whereas the, if you say, well, I'm going to take the x coordinate and then the y coordinate, then you can produce a total ordering. Anyway, so that you have to show that, and then there you go. And then transitive is another property of this, that if x is less than if A is less than B, then B is less than C, and so on. So the proofs for that don't really matter to me. Like I only prove these things because they need to be that. They need to be because the sorting algorithm needs that. Prove that it's sorted, and so like I'm not like, it doesn't really matter what this means. The important thing is like this line, and if you care about the proof, well, you can see, well, you can see what's happening over here. You introduce this rule. You start out with like you have to prove this, then you introduce whatever this means, and then you introduce these A and B variables. Like this is what is total. Like this is how is total is defined. So you have to figure out. You have to introduce some variables for all of these A and B, whatever. So you introduce them, then you say, cases A, cases B, and it's gonna. I'm not sure I actually understand how cases work. Kind of instructive. Usually, hmm. Usually when you use cases, I would think I use by cases, so I don't actually know what cases does. I'll have to look into that. I can do that right now, I guess. Like I'm partially just like explaining all this for my own uh, education. It's very hard to find these things. Like, like here, cases. This is cases with an apostrophe. It's a general purpose tactic for deconstructing hypotheses. H is a hypothesis. Bundles up two pieces. Yeah, that's not what I'm doing. I had one like this one. I had a long list of cases. Did I lose that bookmark? Nope. Just somebody went. These are all the tactics you have available to you. There's like hundreds of them, and some of them like only apply to. You can write your own. Some of them only apply to like certain kinds of uh, of problems or whatever. One goal for each constructor of the inductive type in which target is replaced by a general instance of that constructor. Type of an element in the local context depends on X. That element is reverted and reintroduced afterwards so that the case split affects that hypothesis as well. Cases detects unreachable cases and closes them. All right, so it's like introducing induction on your type. Except I don't see that happening here. Like usually if you put the cursor right here, that's interesting. So it's like expanding this term here. You can see that when you do cases C, it's showing you what is being eliminated here. It's very complicated. You have three. Yeah, so you have two relations here and an implication, like an implication between them. I didn't know that. I guess that's what cases does. So it's just rewriting this term. So we started out with this. Oh, I see. I don't have a natural number. I have a D sequence, which is not which is a structure, right? A sequence is a structure. And so there is no induction hypothesis. You just have to prove it basically for all of them. And the property that you want to prove is that it wants you to prove is that uh, that, that that this value, the D term equals D, but that's what dseq means. There you go. So it's kind of like easy to prove. Um, hmm. Yeah, I'm spending too much time on this. Like this is something I kind of passed over. Like I didn't really pay attention to this. I typed this much, and I'm pretty sure As soon as I did this, oh, maybe not. Yeah, so it generated that for me. That was like one of the few times that Copilot guessed right at a proof. It guessed both of these like almost immediately. Almost every other thing that it generates is just garbage. But I just happen to luck out on these ones. Sometimes it'll generate like a couple steps of a proof and they'll be valid, but like, why did it generate them? Like it didn't really make any sense to do that. All right. Anyway, so maybe I'll just jump ahead, but I do kind of want to review what I've done here. So, all right. So again, we've got the structure, we've got the identity rake, and that just contains the sequence, 0 plus 1n, which is only one item. So of course it's sorted. And then the length of that list is 1. So obviously 1 is greater than 0, or 0 is less than 1. And that's the proof that this is a valid thing. So each instance of this, you cannot construct a rake that does not have a proof of these unless you say the word sorry. Sorry will prove it, but then you get squiggly lines over. Like this file is yellow because I've used the word sorry somewhere way down here. Okay. Anyway, rake term. How do you evaluate this? Well, you have the number of sequences. You just you split this based on the number of sequences length, and so you take this number n. So the nth term is n modulo q, and then we have the proof that that is less than length of the sequence, because that's what modulo means. So now modulo LT is something in the library that proves this for you. This fact. The type of it tells you what the fact is. That for all, that if x and y are numbers, and y is greater than 0, then x mod y is less than 1. And then we can plug in. We can plug in the x and y. So we plug in, plug in whatever it wants here, and then our size here. So because q is somehow that's the proof of this, but I'm not sure I fully understand that. But oh, you're plugging in a hypothesis, right? You're plugging in the hypothesis that so given these two things, oh yes, so the one is implied. So given an x, I'm not entirely sure how to, because like this is a proposition, and somehow that's being passed into here. You can apply this function to this proposition. Like there's no, this is not a tactic. This is just a term, right? And you can do that. Like we can check the type of this anywhere we want. We say check. Oh, so it's this proposition. I see. Oh, right, of course. Right, this is a type. So this is a proposition. This is not code. This is the type of this thing. So it's just this is the type, and then you pass in the, I guess, the x. I'm still not clear enough that I could explain that. Trying to explain things like really brings about how, or brings to the surface how little I understand, right? But I hope I'm not flailing as much as I was last time. I'm still low in early in the learning curve here. All right, so rate greater than equal to. This is going to take. All right, so to finish this up, all this does is once it does the modulo, right? We need this proof in order to to do this operation without like any error checking. We're proving that it's in bounds. That's what this thing is. And then once that proof is there, we don't have to do any error checking here. And then we just check that sequence and pass it, and integer divided by q. So the integer division of q divided by q. Okay, and so that evaluates that. And so this gives you an arithmetic sequence, an aseq, or I guess a dseq. And then now again we've forced it to a function, so we can treat it as a function, and we just pass in this number and we get a result back. And so that's basically eval the entire rake by picking one of the component sequences and then return the value, the calculated value. Okay, rake is greater than or equal to, so that takes a rake and it's going to produce a new rake, and it's going to filter out anything that's less than this number. And so what it's going to do, basically, if this, if the cutoff is here or whatever, then it's going to take the constant and like add it, repeatedly add the constant until to itself, add the constant to the term here. So start with g, and then g, be 2 times g, 3 times g, and so on, until it's greater than this number, or rather until it's greater than. Is that right? No, of course not. It has to be. It's going to just evaluate this thing. So it's going to add 30 times some number plus g and keep adding that. What am I trying to say? I'm not explaining it well, but it's going to keep adding. It's going to keep adding the 30 until it gets to this rate. So because when the difference between these two numbers is 30, because that's what the slope is. G, and then g plus 30 and g plus 30 plus 60 and g plus 90. It's going to keep adding 30 until we get higher than the cutoff, right? So that's how you would truncate this. That's how you would chop it off here and only have numbers above that by just moving the term up. So that's what greater than or equal does. And actually, that's what, the arithmetic sequences can do that themselves, and so we delegate that work to the arithmetic sequences. And because of that, obviously some of them, like if you cut it off in the middle here, some of them are already above that number. Some of them move up, some of them don't, and you have to sort it. And so we have to pass it to list merge sort and resort that list. And then now we have to prove that it's sorted. And I had, in order to do this simple line that says, okay, well, there's a fact that if you sort it, it's sorted. You first have to prove all these things. And so that took me a little bit of research to do. Then it was easy. And then the size, you have to say, well, okay. Now that it's sorted, you have to, get that sort out of the way, so you simplify it, and then the size is maintained. That's the proof. Every time because we're returning a rake, so we always have to prove this. Any function that returns a rake has to prove these things. And these are pretty easy to prove, right? The list is not empty, and it's sorted. That's it. And you sort it by doing this, and then that's it. So it's always the same proof. These proofs are always the same. In fact, probably you could. I was gonna say probably you could pass this in here. I could do a merge sort here in the default, and then every time you did a merge sort, then that would be the that would handle it. But you wouldn't have access to the word R here. You'd have to change this a little bit. Oh, and in fact, this is referring to this. Okay. Right. It's referring to the input. So the input is, the input has a size, and the output has the same size, and so you can refer to the input to get a proof that the output is the same size. or the output is not empty, because merge sort preserves that property. Okay, so rem would then be the notion that we're going to remove everything that is, actually I copied and pasted, this is not even correct, but it should be the exact same thing, except we're going to use the word rem here. And rem does not work, so that's something I have to implement. Oh, but we can't. All right, because you can't. Okay, so now, yeah, so that's actually something different. All right, so given a sequence, all right, we'll come back to that. I'm going to leave this red here so that I know to come back to it, because this is the next thing I have to do. Well, maybe. Maybe I just put the word sorry here. How about we just say merge? Yeah, I don't know what I'm doing. I don't know why I'm doing this. We'll just mark this off. So it's, why is that red? Sure, why that's red. Oh, because I lost the curly brace. Okay, so the curly brace to end the rake. All right, so now on top of that structure, like I wanted this to be like one structure, but like it just seems like it's easier to break like your implementation and your proof into two different things. So you would never really use a rake by itself. I mean, you can, but if you want the proof, you also want the rake map, and the rake map is just a rake plus a proof that the rake is preserving some property. And so here's the proof, right? And the property is a type. So again, a proposition is a type, and so we can say, I want to model the entire set of natural numbers, and so you would write that as a set comprehension like this, like so like S is a nat where true, right? So def all nats equals this. You don't really need this S, I guess. You have to say it's a proposition and true. Maybe you have to give it. Huh? It doesn't. So okay. Really, you would write. Normally, you would just write this as nat, right? Because that is the set. But this is the same thing. So you could say example. We can prove this example. You can't really prove it, can you? You could say like. So if x is in nat, same thing, left, right. Say for all x, what do you say, h? Like you have to have a variable, right? Maybe I can't say this. I mean, you can say, I don't know how to say this. I think you can say it. Okay, for all x, x is the same as x is in s nat where true. I think you can't say this without going up to like a higher level of. Right, because this is about a type. All right, so I don't know what I'm saying. I don't know. This is something I don't understand yet about dependent type theory. I don't know how to express this, and I'm not going to get into it right now. I admit defeat. This happens a lot, right? I'm still learning a lot of this stuff, and I don't have it in my head yet, but I can make things happen. All right. So anyway, we're coupling it. So this is saying, given an n, we're going to ask given a number, we have to determine whether or not we want to accept it into the set or not. And so, again, this is representing the set of all natural numbers. The proposition represents that set because it's true. Like it's never going to filter anything out. So is it in the question is this in the set? And the function returns a result, and the result is always true. So then everything is in the set. Every number you pass in is in the set. And so this is a proof that for every number that you pass in, you get a number out, and that's what term does. And it's actually looking at the sequence 0, 1 because it knows what IDR is. IDR is defined as the identity rake that has this particular sequence in it, and it can prove that the number it gets in that gets is the same thing as getting out, right? So like these little steps are enough to make that happen. Okay, this I proved earlier today. This says that if you have a rake map and it produces a term, so if you feed in some m and you get back an n, then that means that one of the sequences has some other m that if you passed it in, because again we do the mod length of a number of sequences, then you would get back that same number. So one of the sequences is producing that thing. This says there exists at least one sequence, and it's exactly one. And I don't know how to state that yet. I don't know how to state that in. Is there like x1? No, because you can say like x5 and it's not a thing. I think e exclamation point is what I want. Point is that they're unique, right? So this might not be enough to prove what I wanted to prove. And what I wanted to prove is that the idea here is that later on this operation, GTE does what I say, like moves things up. But then the other one is rem, is remove multiples of a prime. Like once your slope is a multiple of a prime, then either every item in the list is going to be a multiple, again, like the evens, right? The evens are 0 plus 2n, so every single one of them is a multiple of 2, which is prime, or none of the items. Like you'll never have 1 plus 2n will never produce a multiple of 2. Likewise, when you say 3 plus 0 plus 3n always produces multiples of 3 by definition. 1 plus 3n will never produce a multiple of 3. 2 plus 3n will never produce a multiple of 3. It produces multiples of 5. First one being 5. Sorry. What am I saying? Yeah, 3 times 3 times 1 plus 2 is 5, right? 3 times 2 plus 3 is 6, right? So that one gets marked out. You know, 3 times n plus 3 is going to be 3 times n plus 1, right? So it always produces a multiple of whatever. And so I wanted to prove that. What am I trying to say? I wanted to make the assertion that if I remove that item, then the sequence doesn't exist anymore. And I don't know if this is necessary. I don't know if this thing is necessary. I got ahead of myself. I thought I might need this. I made the statement that if, you know, I don't know if I really need it or not, but like I learned how to prove it. And this should be REMSame. And then I came up with this proof and kind of worked my way backwards. Once I had the proof, I kind of refactored it until I had these 3 laws that they all follow. So this is not based, like this is based on call them conjectures right now because they're not proven, but they're, you know, they're based on these propositions that are proven by the word sorry right now. So I need to prove them. So that's, all these yellow lines are things I need to do. So this says, and these are exactly the same. They're both like, these 3 things both say that, or that, you know, they say for this operation, the greater than equal operation, you know, here's the proposition that we're looking at. If n is less, so we're passing in a value p, and then n is the result type, right? So if we say, so we take the rake map, we take the rake, and we say greater than or equal to p, then all the terms are now going to be greater than or equal to p. So if n is less than p, n being the output, right? Term n equals n. If the output is less than p, then there does not exist an input that will produce that output. There does not exist an m that will produce the n. And so that's the rule, that we drop all the, because it's not reachable, like it's as if we've removed those numbers from the set. Right, and so when we implement GTE, what we're doing, we're going to take a rake map that has some property that describes what's in the set. It has some Boolean expression, you know, that looks at a natural number and says, yet true or false, this is in the set. Whatever that property is, we maintain it, right? We maintain it, and we introduce the property that the output, right? The output number, the number in the set, is greater than or equal to p. So only if a number has the old property and this new property is it going to be reachable from this rake map. And again, so like that's implemented in the rake, and then the rake map adds the proof on top. So like this is the formal verification that it works. And so this is greater than or equal. This is rem being remove a prime. Remove multiples of a prime. And so here they're exactly the same, except now the assertion is, or the proposition to look at is that p divides n or not p divides n. And so this one says if the new property holds, then there does not exist in the new rake, there does not exist any way to reach that number. Sorry, if the new property does not hold for a number, and there's no way to generate that number from the rake map. And so my thought is, well, okay, as a step, I can say, well, okay, none of the sequences using this, I can say, well, there has to be a sequence that generates that number. And then I can say, well, none of the sequences have this property because of such and such. Right? So that's kind of the next, that was kind of the idea behind this. I haven't used it yet. It may turn out I need a different statement. So we drop all the terms that are less than p for greater than. Here we keep all the terms that are greater than or equal to p. So if there is a number such that n is a natural number that n is greater than p, and we used to have that number in the set, so the previous rake, the RM rake term previous m, there was a previous input that produced that number, then we still have a number. So we have a new number m. It's not going to be the same number, but some other number is now an input that we can use to produce this number. And then finally, so we dropped the ones we wanted to drop, we kept the ones we wanted to keep, and then we didn't add anything. So you got to make sure that you didn't add anything to the set, so that no other number creeped in. And so then it says if in the original one, or sorry, if it exists now, it also exists. There was a previous input that produced it on the previous rake. So if it exists now, that implies that, if it's in the set now, that implies that it already was in the set, and so this is a filter. So it introduces nothing new. And if we can't prove this, then that means that we might have allowed something to slip in. So that's that. So we're going to prove these three properties. And then the exact same thing when because both of them are, this is removing numbers less than something, this is removing numbers that are a multiple of a prime, same thing happens. And in practice, the way you detect it is you do this partitioning step, and then you just filter out the lines that as I said, they either always or never produce multiples of the prime, and partition is multiplying by the prime. So there you go. That's what happens. Anyway, so we have these three lemmas for each one, or laws or whatever, and then the proofs for these are basically exactly the same. And really, all this is doing, so they're all proved by Aesop, and which I think stands for. It has a funny name. It's like automated something of automated something search or semi-obvious semi-obvious propositions, semi-obvious proofs. Automated extensible search for obvious proofs. Yeah, so you can tag a thing and use it to find proofs of things, which I didn't know before. So I've learned a lot of things that will generate proofs for you. But you don't have to do a lot of tedious work anymore. And in fact, basically what this is saying is, to prove that we have the old prop, we're going to say that, first of all, we're just going to give names instead of having to write this out every time that this exists, previous and exists, current. So this is just a proposition. It could be true, could be false, could be anything. Like you can say, let H7 prop. So the type of H7 is a proposition, and the value is 7 equals 3, right? Obviously, that's not true, but you can have that proposition, and then later you can, use it to simplify something in one of your expressions. So basically, this is acting like a macro, so that every time I say HM here, it's as if that were pasted in there. So HM is just the proposition, no truth value attached to it, no proof attached to it. That it's just a name for this thing, that there existed an M that produced the number that we care about. What are we proving? We're proving that there's a bijection. So again, it's this. We're proving this, that this property takes an n, and if that, we're introducing here, for all n, this property holds if the rake map, and that property was true of everything in the previous rake map. So again, we have a proposition that the value is reachable now. By providing some m, we get the n out, and which may be true or false, and for a given n, and then because it's parameterized on n, and then same thing for this one. We have a I'm trying to find a place to put the cursor that it doesn't put these big pop-up things. But yeah, same thing. So now it's in the set now, and it previously was in the set. And then so we have to show that the proposition itself is equivalent to HPM, right? And that's provable by the hypothesis, the proof that is on the rake itself that says there's a bijection. I'm sorry, on the rake map itself it says there's a bijection. That proof involves this says prop is true for every member inside. We get that for free because from the input, because the input is already checked for us. So it's like induction. And then, if n is less than p, then there is not a way to do it. That's the whole thing that we have to prove up here. That basically we're basically these three laws that I have not proven make all this work. So we say by this law that I haven't proven, we just plug in the values, previous and p and n, previous, and then p is the natural number that we're filling in. Then n is the for all n here that it asks us for all n, prop n, and then we introduce n, so n is now a variable that we just introduce them. That's a proof technique to get rid of the for all. Anyway, so these laws are what allow us to they fill up all this stuff, and then we have to prove this statement, which is the kind of the goal here that it generated for us, right? That we need to put in for the new bijection, right? We have to prove that this new bijection exists, and that's what the statement is. Like that's generated, like that's what the type of HBIJ is. Is that given this proposition, prop n and right here, prop n and n is greater than or equal to p, which is right here, is equivalent to there's some term that you can plug into the rake map to get that number out. So if these things hold, which we don't know if they hold or not because I haven't proven them yet, but hopefully they hold because that's what the intent is, then this proof is accurate. So this proof type checks, and the actual proof, ESOP can look at these facts and say, okay, this all checks out, and it actually produces a term that composes a value of this type right here. Sorry, of this type. It composes a value of this type. This whole thing is a type, which is a proposition, and it produces a value, and a value and a proof are like the same thing. So ESOP is able to construct a program that generates that type given all this information. And you see, like basically a lemma and a theorem are the same, are the same as a function. Right? The whole point of this. And the structure of these are exactly the same, except everywhere this one says n less than p, this one, or n greater than or equal to p, this one says p divides n and not p divides n. So these laws are exactly the same, except again for that thing. And probably there's a way to generate this code, but since there's only two functions I need, I just haven't worried about that. I haven't messed with that yet. And these are going to be very different. The proofs of these things are probably going to be very different, because this has to do with one property of arithmetic sequence. Actually, maybe they'd be very similar, just with the say async.gt and async.rem or whatever. Except but you wouldn't remove. This is removing things from an arithmetic sequence, whereas this is removing an entire arithmetic sequence. And there has to be a step before that partitions the arithmetic sequence into lots of other ones, because you can't. That's the only way you can take out one. So that's kind of that's why these are all going to be different structures. It may be the case that the structure of each one of these three is very similar, and each one of these three is very similar. I don't know yet. But what I've learned is that it takes a long time to prove these things, at least for me. Maybe that's a skill issue. Probably is a skill issue. I am getting faster at it. But what I have learned is this general technique of try and prove something that you want to prove as if these things were true. Now, if these things are false, like if I've misstated this, I have a problem, and I'm going to have to go back and correct, any proof that depends on it. And so the mistake will bubble upstream or downstream, I guess. So ideally, like you have all the things that you want to, like all the facts that your proof depends on are already proven for you, and so you have a nice little tree of proofs, and there's no problem associated with it. But because each one of these is difficult to prove or takes a lot of time to prove, you want to be very certain that you actually need this proof. So I know that to prove these statements, which I'm almost 100% sure are the statements I need to make to prove that I can implement a prime sieve with this. But I want to make very sure of that. Like I want to actually go prove that. So I'm going to pretend that these are proven, and I'm going to use this fact to go prove these two facts. These two, they're not really facts, but the fact that I guess it's really this thing, right? That when I call this function, I get back this proof that the property I want is, that there's a bijection between the data in this rake, this list of arithmetic sequences, and the set of numbers that I want to have. So whatever the set was, and now they're greater than this number, so filter out anything less, and this one to filter out all the ones that are a multiple of a prime. And I think between these two things and the base case, which is this identity rake, right? So this one sequence right here, that just starting with this, we know that this maps every number from, actually this is here GTE greater than or equal to 2 has already been applied, but there would be like 1 and 0 down here somewhere, and then this line represents every single natural number from 0 to infinity, to as high as you want to go. And then now that we've applied GTE 2 greater than or equal to 2, I have to prove that I have, like, I've somehow captured every number greater than or equal to 2, right? Every natural number greater than or equal to 2. And then, right? And so now the next step, okay, well, I want to say, well, I know 2 is prime, so give me the things that are, break it into, to basically multiply this line by 2, and then the picture is, this would show, this shows all the odd numbers right now. So I jumped from every number to all the odd numbers, and what you didn't see between these two pictures is that this line split into 2 lines that were all the evens and all the odds. So all the even points moved left onto one line, and all the odd points moved left onto a different line, and they both have a different slope, and they're 2 parallel lines, a dot here and a dot right above it. So 0 at 2, so 2n plus 0 is 2, and then 3 would be right here. Sorry, this is right here. So we've moved from 2x plus 2, this is the number 4. Wait, what? That can't be right. Yes, it's right. Okay. This is not the number 4. This is the number 3. This is these numbers. But we had 2x plus, we started with 1x plus 2 with 1. We filtered it up to 2, and now when we apply, so we're gonna take the numbers. I gotta have this is so simple in my head, but it's like hard to put into words. And so I'm gonna have a nice animation when I do the video. Whatever. Anyway, this line splits all the, and each dot goes, the even ones go to one line, the odd ones go to yet another line. You get two parallel lines that are separated by 1, 2x plus 0, 2x plus 1, two parallel lines. You cross out all the zeros because they're all multiples of 2, the even numbers, and then you are left with the odd numbers. That's what we're seeing. Same thing here. We break it into 3 lines, and 2 of them are left. Here we break it into 5 lines, and 4 of them are sorry. Yeah. Here we have 2 lines that we took. I need a video here, an animation here. I thought this would help. Last time I just did like little sketches. It does not help. It's just not easy to explain this without motion. Anyway, line split up, blah, blah, blah. Okay, so anyway, I believe I can prove this. That if I look at any one of these sequences, the lowest term is a prime number, obviously 7, because we stripped out multiples of everything else. The lowest term is always prime. We obtain it, and we're ready to go. So that is going to be an implementation called LeanSieve. Sorry, I always say that word is sieve, but it's not. It's sieve. And that is a completely different theory over here that I think I talked about last time, so I'm not going to go over it again. But we have, I'm going to go over it a little bit just to refresh my memory. We have n prime is just the natural numbers that are prime, and we can coerce it to a natural number, and we can divide it and all those things and work with it just like any other number. You can see if it's less than or equal. This is a fact about primes that I've proven that may not be required. Or I was trying to work from the top down, and I finally basically generated this. A lot of junk in here, but basically the idea, at one point, like I was working from the top down, I was trying to say, what does a general prime sieve look like? And the kind of idea is that you have some way of tracking a set of known primes. So a prime gen has a current prime. You can initialize the prime generator. You can get the next state, and there's somewhere in the state, there is this associated set that is all the primes less than C, the current prime that you're looking at, which might be empty if you're looking at 2, right? There's no prime less than 2. And then given that number, there's this. It's all the numbers that are greater than or equal to 2, and the number and that none of the primes divide that number. If you don't have greater than or equal than 2 there, then you can have like, eval like 5. This is backslash, get this little Unicode div thing. Like 5 divides 0, true. 5 divides 1 is false. Right? So that means that because this is false, right, we say not 5 divides 1, then that's true, and that means 1 would be in the set, and so we have to say it's greater than or equal to 2. Or we could say greater than 0 or whatever, or greater than 1. Okay. So this was a different way of formulating that. And so I was trying to come up with the notion that like a prime sieve is something that uses these facts and says, okay, now I'm going to take the minimum value out of this set of remaining numbers, and that minimum number is going to be prime for the following reasons, and then I can prove that. And I think this, right, because we're saying it has no prime factors, like I think you need a few other things. You need like where did I put it here? This is what you need. Right, so I was kind of floundering here, trying to figure out what the right things to do were. So I had these, and later I simplified it and said, well, you know what? am I describing a prime sieve or a prime generator? And I came up with the idea, okay, here's a prime generator that is not a sieve, right? It's just doing trial division. So the way this works is you start with the number 2. That's the initial state. Is just the number 2. Uh, so oh, sorry. So simple gen is the structure, right? So simple gen start. It just all the entire state is it has a value named c, and c is prime, and that's it. That's all we know about it. And the way we get the current prime is we just look at that number, and then the way we implement the initial state is to just put the number in 2, and so we still have to prove prime gen that this is prime. So we need a proof that whatever number we generate here is prime. And then whenever we construct, this is a class where it's simple. Oh, no, right, no, that's true. Right, so init is something that produces the value of this type. So a prime gen, some type alpha, where init produces an alpha. So init produces one of these, and we're implicitly passing the value c to that 2 there. So it's just, you could say c. You could do it like this: c equals this. But either way, you still have to provide this proof that that 2 is prime. And so you need this type, which is the assertion that is proven somewhere. Because there's a value of this type. You need a value of this type that says that 2 is prime. And so somewhere in this file, like, this is proven. I wonder what the proof is. And it's loading. Anyway, so you don't need this. This is simple enough that we did that. And then what is the next prime? Well, we just, again, make a new one of these with c set to this, n prime gt, n prime greater than next n prime. So this is a value of this type, like prime gt. So prime gt, where did that come from? Is a type, and it's given a type c, given a number c. The type is all the natural numbers that are prime gt's, which is a prime. So all the natural numbers, and they're greater than c. So p is a not prime p, and c is greater than p. So prime greater than c. This is the proposition that takes this argument, right? So then we say, or takes these 2 arguments. So we say, so given this in the type, the type is prime greater than c, and then the value is prime greater than c. So this is set notation again. And this is, I forget what this term, it's a subtype, right? So it's not a set it's not a set comprehension, but it's something like that, subtype. So this actually, I thought this would do the search twice. It does, but one is at file time. So natural numbers have this thing called find associated with them, and if you can prove that this is decidable, so instance decidable, this prime greater than is decidable by inference, like it's able to prove it for me, so I don't have to worry about why it's decidable. But in general, it can say, is it prime and is it less than this number? It can look at those 2 things and say yes or no. So that's decidable. And so at runtime, we can actually calculate this. And So this winds up being like where's the actual thing? So the next prime is a natural number prime greater than next prime GTs. It is a little complicated. I probably should clean this up a little bit. Can clean this up a little bit. But I think like this right here is a proof that exists primes greater than C, right? It relies on the fact that there are an infinite number of primes to generate this proof, and then if you give it that, then NatFind will actually go find the number for you. It might take forever, but it'll look for that number for you. Fine. Is this ever used? No, because it's the exact same thing here. I could use it here, right? What's up? Yeah, I'm. What's up? My door opens. That makes a loud noise. I'm tempted to just get rid of this, but n prime GT. I'm just kind of refactoring here. Right, so this is what I actually want to prove is that we have init and we have next. But I thought I could have sworn I had a requirement here that like the next prime was not like there did not exist a prime that was in between them. But it doesn't look like that. I think I may have optimized this away somewhere. Or maybe it was just like trivial because one is the minimum value or something like that. Somewhere it's like minimal. Somewhere I had this statement that maybe I was moving it into here. Let's see. Like at this time I hadn't learned how to like clean this up, right? So I had a lot of junk here, and it wasn't easy to see what the. Oh, and there's no prime between them. Yeah, so this is what I was looking for. So really, the two facts that I want to prove are these, and I had tricked myself into thinking that we had this here. No, I just never proved this because it's obvious from the fact that I'm using nat find. Like nat find spec actually has this. Nat find spec is, doesn't say, but yeah, nat find spec is the proof that it satisfies, and then there should be find min. And I guess I never did that, but it is. You know, I could trust that. So really, I've only proven for this one. I've only proven that these facts right here. Like I've proven that. So prime gen says that C produces a prime. That's it. And it really should require you to prove these things, these two things. And so I switched it to like prime sieve spec or whatever, but right. And here I'm talking about these R's and S's and everything. So S is the set of primes, R is the set of the remainder, and C is the current prime. And yeah, so previously this had been called like this prime gen had been called like prime sieve or whatever. And so I'm trying to get to the point where like these are two separate ideas. So I have prime gen and prime sieve now, but prime sieve is just an empty file. And the thought was that these things that it's talking about here, so prime gen is going to have n prime in it, and have this. This is the idea of what a sieve is, that if you have no prime factors, then that implies that there are no factors at all. And so that is like kind of the core theorem of a sieve. That if you mark off the multiples of primes, then right, you have no, you'll have no compound numbers left. Right? Why is this? Does it say? Has already been declared because okay, so I'm moving it into this file. So we don't need this. We don't need this. These are not necessary for primes less than C, naturals less than C, primes less than C, natural numbers co-prime to some known primes. None of that is. I'm getting into what I actually wanted to prove. Now, what's wrong with this? Already been defined. I'm going to complain. All right, so set of known primes, we don't talk about that. The whole point of this little simple generator was to demonstrate that, like, to help me in my mind clear the difference between a prime generator and a prime sieve, because not all generators of primes are sieves. There could be any number of algorithms out there that produce primes that are not, you would call it. I think everything below here is something that I want to say about sieves, if I want to say it at all. All right, so then let's actually do this. I think I can put this inside of here. All right, so from the bottom up here, I'm proving that I have a simple generator. So so we'll say def g is equal to simplegen.init. Why is that not working? Because it's in this section, okay? Okay, namespace simplegen, is that how this works? Maybe I just maybe we do it like that. Instead of a section, we use a namespace. But I still can't find it. Oh. I think this is right, and it just hasn't caught up yet. Oh, maybe not. I have to say open simple gen here. Do I have to give this a name? No. I don't know what this is all about. I'm just gonna not do this for now. Do I have to say prime gen, simple gen? Why can I not call it? This I'm I'm doing something stupid here. Ah, okay. All right, so the trick there was that. All right, so then can we say so we'd say term G, right? Term it's not term next. So G next. I didn't actually generate a sequence from this. So G dot next. Why not? You have to say open prime gen. Have I never done this before? So if I say G is a simple gen, then if I have a type there, G.C, it should be 2, right? Or does it not know? 3 variables. Okay, so if we say init, I think what we want to say is, I think to make this, we say simple gen init, so def gen init, and that is going to simple gen equals that, and then here we say gen init. So then it has to be synthesized. This instance instructs Lean on how to display the resulting value. Deriving data repr. There we go. So now we say C equals 2. You have to say prime, and you have to say the same thing here. Prime gen.next G works. It gives me C equals 3. Then we say prime gen.next, oops, next G is 5. Okay. And then is there like a? Let's ask Copilot. Can I? How to recursively apply a function n times mean? I could write that myself, but I think there's probably a built-in thing. So let's see what Copilot is very. Yeah, I could do that, but like, what's the idiomatic way to recursively apply a function in Lean 4? Come on. I don't usually use this little thing. Lean 4 built-in function to apply. Maybe this might not exist. Like, string library doesn't have a bunch of stuff that you would expect to be there. But coming from J, I expect this to be in a library. Apply a function n times. Or mathlib function. Iterate is probably the word I'm looking for. So all this garbage, like, it doesn't. So we say check iterate. Oh. Okay, well, maybe that just doesn't exist. Let's just write it. What it gave me before is not like iter. Oh, what is this now? That doesn't look right. It does not iterate. Iterate a function. The op is A to A. It's iter. Not. I don't know what that does. Gen n prime. Okay, so iter n. Oh, it's this function. It's picking up this function that I'm inside of. If n equals 0, then we're going to return we want t is a type. Or do we want it a prime gen? So we say prime gen alpha, right? Some type t is prime gen alpha. And n times, we're going to give it, right? So we want like, do we have to say rec? So let, I'm going to ask Copilot for this. Like, so okay, so we want the base case would be, what am I trying to do? I want to define a function inside of this function. Def ox is going to be t t because we had, I'm thinking recursively. You want to work down to the base case, but then you want to start with the base case here. You could. It's been a while since I did this. Let's see. So if we want to else, just comment this out. Given a natural else, we're going to do iter of next. Just calling this function prime gen. Say t dot init. Yeah, that didn't work. T dot next. And we wouldn't want to do that. You'd want to have a list of these things. So right, and but this is only going to, okay, so this is, we want to return like an accumulator. So we want to say t dot init and let t equals t init and then return the list. T dot c. I don't know why you can't do dot c for that. I mean, you could just return the list of prime gen, but like, and then map the. Say, with def ox is a t. It goes from t nat and it's going to return new t and a list of primes that it's got. And right, so we pass it in t init and 0. What's wrong with that? I'm not sure what's wrong with that. Failed to synthesize prime gen t. Oh, maybe want an alpha? what is the problem here? Is it kind of do depth inside of it? Okay, so okay, so we'll say PG is that it's a prime gen of some type T, or I'm calling it T here, alpha. All right, so then it's all garbage. Okay, that's what I want. So start with the prime gen. Take the natural number. We start with 0. This part is right. This is wrong. No, it's not right. Else we're going to say ox g next g eg minus 1. Else say let, we want the A and the list of primes. I'm not used to thinking about it this way. Is equal to, I have to say rec here. All right, so n minus 1, and then we're going to return, so we'll call this g prime. So we're going to intercept that. So that's what we want. But now we're going to say, yes, g prime. That's exactly it. So we're going to take the current value and then append it to the. I'm assuming that's the append. That's it. Okay, and then we're going to return unit, and then we want to reverse it. And so then instead of all this, we can just say iter but we want to, so it's really like A is a type, and we can infer that it is a prime gen. I don't even think we need to name this. Oh, we do. PG. Then now this works. Okay, so that's close. I see. So let's hang on. So we're going to pass in the one that we give it, e and n minus 1, and then we're going to say, so we're going to return the one that so right, so we pass it unchanged all the way down, so we get to 0, return it unchanged, and then and then return G prime next, right? We say next G prime, and now what do we get? Yes, that's almost. Okay, G prime prime, fine. And then G prime prime, that's weird. This seems wrong. Like, why would I have to do it? This is gonna work, but I think there's I think you can say it like this: A type and PG prime gen alpha. I think there's like a much more straightforward way to say this. List in prime equal to, you say mute, right? Yeah, mutable, yes. Res is equal to that. Nope. Mute res. Hmm. I don't think you can reassign it, can you? What happens here? What's wrong here? But that's not equality. That's not an assignment. That is equality. How about we just do it this way? Pass in a list of primes. I really suspect there's like a way to do this without, like, I'm not used to like writing recursive functions this way because it's always like abstracted away for you. We want a list of primes, a list of all right, so we're going to return at each step. We're going to return so if n is 0, we're going to return that, and otherwise we're going to return. Yeah, that's it. making this overly complicated in my prime. So n prime. Hmm. There's some way to say that. It's easier. It's not that. We must say this. Oh, come on. Failed to prove the index is valid. You have to put like a exclamation point, question mark on it or something. Oh, it is second. Okay, sorry. I'm confusing myself because we're returning this pair. The n goes away. All right, so we pass in n minus 1, we get to 0. Maybe I didn't buy myself anything. I'm like iterate the iterate. What do I really want? I want something that takes a function from a to a, right? So okay. F J calls this power, but so F power something like that. Now, again, I think this exists, right? We're going to take a function from a to a, alpha to alpha. So the f is a function from alpha to alpha, and we're going to take an initial value. So like x0 would be, you even do a subscript 0, going to be an alpha. We're going to take that from alpha to alpha, and then we're going to take n times, right? Yeah, but you want n to be the last, you want x0 to be the last parameter. We're going to say n is a natural number, and we're going to apply this that many times, and then we're going to produce another a. That's all I really want. Oh no, but I want a list of a's. A list of a. All right, so I don't want x. This is like a range function right now. Say like val f pow, and we just even like a 10, and it returns like 5 or something. 10, 0. Yeah, it just, oh, no, it did return 5. It's not an iterator. Okay, I'm not. Why would that be the case? Oh, because we pass in the x. I see. Oh, this is right then. So if we said x plus or n plus 1, that should count to 10. It does, but backwards. All right, so and then we just pipe it through reverse. What is nat.iter? Check nat.iter. Iterate. That, it's exactly that. Nat iterate. Iterate. I'm going to say, what is it? First the operation. Oh, I see. Right. What I wanted was this, but it's complicated because of the fact that I don't just have a type. I have the iterator at each step. So what I'm going to get back is a list of iterators, and then I want, and so then I want to like, so given a generator, you can say fun here too. Fun G next G, right? Is prime gen A gen A. What's wrong with that? You have to say all this crap. Let's say that A is a type. You say that? No. Can't say let here, right? You have to say gen. Gen init, and then so now next G prime gen dot next. But yeah, pass it in G0 and it knows what type it is now. Equals 31. So that's saying that's the 10th prime. 2, 5 is 13. So 2, 1, 0 is, I'm looking here. I'm looking up there. And I'm typing here. So 0, change that to 1, I get 3, 5, 13, 4. Okay. So iterate doesn't, okay, it does not do the same thing. It does almost the same thing. If I say now iter, that didn't work. Oh, because I have this broken iter in the middle. 10G0. What's wrong with that? Wrong order? Oh, because now we're not doing a. I said fpal is what I was thinking of. Fpal. Right now we have all of them. It's just interesting that it came up with 31 before. The other one came up with 31. Probably because it says n here. I'm not sure. If I just say 3, what do I get? Right. This is what I expect. So I'm not. I'm okay with that. Oh, so 0 returns nothing. That's so 0 should be the base case. Yeah. Guess that is wrong. So 0 should return the initial. So we say x. Now it works. 0, 1. Kind of like this better than like a REPL in some ways. There we go. That's what I. Okay, that's right. And so then we can say primes. Do we need this anymore? It was a fun exercise. Better. Right, so now we'll say primes. F primes is going to be the composition of these. So it'll be F pal so it's going to be a lambda, or we'll say function of n, and it's going to be F pal this whole thing. Except we replace 10 with n, and g with simple gen.init. And then we say primes 10. We can even say this is n is a nat equals say, we'll actually give it a list. But we don't have to do this. Say list of n prime, and now that doesn't work, and we're going to say, can we pipe it through map? Yeah, map. Yeah, that's it, exactly it. So we'll get the C out of there. And what do we get? Not evaluate, huh? I do not understand that at all. That seems right to me. Like check primes. Expected no space before. There we go. I was missing this little character. I did type dot. I don't know what that does. Huh. Okay, that makes more sense. This is what I was. Let's even pass in like what the we want the type to be. Say like alpha here. And A is going to be, sorry, alpha is a type, and we'll have the implicit uh, prime gen A. We have to say PG in it. Yeah. And so then we would say simple gen here. Oh, that did not work. Primes. There we go. I kind of like that. Not sure I'm thrilled about this. But evaluate function power, we'll call it. Function power, apply fn times to x0, oops, x sub 0, and collect the results. Recursively n times to x0 and collect the result. Ow! Don't think I need this. All of that was just to return this into a generator, but now I can do, now if I have a prime sieve then I can do the same thing here. I know I use the name tangent storm for a reason, right? I go off on tangents. That's not the reason, but But, this was a side quest, but do I need this? I'm curious. No, I do need that. No, I think now that I have this, I don't need to refer to this explicitly. Yeah, I don't. Right, so we can just print that. There we go. Oh, I'm just curious now. It's like complete side quest here. Lemma, or we'll say example. Maybe we don't need to keep this, but just example. N. So n is a natural number, and this is equal to, yes, exactly. Did that work before? And it proved that by induction, but my ESOP cannot find it. So it says it proved that with induction on n. Yeah, okay. You say list.range. I'm just curious how difficult it would be to list.range.loop. I bet list.range is very similar. Well, it would have to be. It would have to be very similar. Loop n, where loop. Oh, it's interesting. Instead of saying n minus 1, but why isn't this reversed? So let's see why it's not reversed. Oh no, in the middle of the night in Sweden, and we have to get up early tomorrow. Will you post this so we can view it tomorrow? Yeah. Hello. Well, thanks for watching. This is. If you want to listen to me ramble, this is all recorded, and it'll just be on this channel. So when this is done, it'll be a live recording, or it'll be a recording. Why isn't this? Why is this not backwards? So we say loop n, and we pass in a number. Oh, so loop is a function that takes a natural number and a list of natural numbers and returns a list of natural numbers. Oh, because it does. Yeah. Okay. So this. Yeah. Obviously. Man, I haven't done this since. I mean, I never really took a class on this, but it's been a long time since I had to do these manually. So what did I do here? Instead of reversing it here, uh, wait, wait, what? Where did that just go? Back here. Thanks for watching me ramble about this. I'm not looking. I'm trying to see all the things I have open. Did I just close that file? Is that my problem? Yeah, I closed the file, so I can't see it. So what was I looking at? I was looking at list.range, right? Um, oh, that's interesting. I would have expected. To me, iota is this function. They call it iota n is counting down. So this is actually kind of interesting that you've got the two directions. So this one starts at m. Oh, I didn't know you could do this. This is, in Haskell. This is a pattern capturing thing. Pattern capturing value capturing pattern or something like that. So this is assigning. I guess it's the same as in Rust too. I think you can do this in Rust. So m is matching this pattern n plus one. Which I guess is syntactic sugar for the two cases of. That's interesting. Like you don't even need like a match statement. But here you're passing in. So range 5, you get loop 5 empty. So that's 4 plus 1 empty. Loop. So it recursively calls this loop 3 plus 1. Oh, I see. So it just places the 4 there. Like I say, I see that, but then as soon as I'm looking at basic.lean. Okay. Like, what is that? As soon as I switch over to my code, I don't. It no longer makes sense to me. I get confused by what I see in my code. I'm almost positive that this function right here has some name inside of. In fact, I bet if I look on Google, I can find this. I bet if I go to Google, is Google, and I type this in, maybe I can find this. No, they are matched in any order. Right, but you have to give them weird names like this. So we'll call this like F, A, to an A, and then N is a gnat. Then X is A, and then A, and we're going to get back a list A. Didn't like that. Interesting. So a function and a nat and a lot of these things, but I'm expecting to find one in like basic or huh? It could be the order is different, right? Interesting. That okay. Well, yeah, I'm not good at finding this iter. Find iter or iter or f pow. We're gonna of pow, but not f. I don't know. All right. Yeah, I just like. I mean, like I'm spoiled, right? Because like, one of the things I want to do someday is I want to get like J notation into this. I use a language called J, and if you say like, this is gonna look weird, but like you say 5, that returns. Okay, so say 5, that returns 6. So you can say, I mean, you can already say like this and get the range, but I dot is that. But you can say this. So this being the increment function, and you can say I want to do it 10 times, and you give it the number 0, then you get 10 back. And if you put a box around the 10, like you and wrap it in a list, then you get all the numbers. So you can implement. Anyways, this is called power. You can see it's kind of orange as opposed to green for the other. These are green verbs, and this is an orange verb. So that you know kind of meant to be like reflective of this, where you're saying double 5 times some number, right? All right, colon, colon, and you get the same thing. Anyway, so like I'm spoiled by having that like is like a built-in. Rambling since the Raycast interview got me started in taking. Oh, Dean looks scary. Oh, I'm so glad for. I'm glad that was helpful. Uh, yeah, Jay is. I've always wanted like one of my interests in Jay is that it's good language. In Iverson's original paper on APL, when he talked about his Turing Award lecture, notation as a tool of thought, he talks about one of the things you want from a notation is that it's amenable to formal proof. And he gives an example of like using APL to, to write a proof where you're like modifying, from line to line, a calculational proof, which Dean is very good at. Um, but you know, but Lean does not support the syntax of APL, and so I wanted to combine those two things. And I know that you can override the syntax in Lean to some extent, but I haven't really explored that yet. But that's something I want to do someday, is to like write a J or APL kind of dialect of Lean, and be able to write proofs about that. The Neal language, Neal. Uh, like the manual came with a bunch of proofs in it. I thought that was neat. Okay, so anyway, what was I doing here? I was just I was gonna try and prove this, and I think I'm gonna give up on that. That's beyond my abilities right now. I think this is definitely provable. Um, oh, but then I wanted to see what I could do to fix this without. Oh, I see why it's different though, because in in range, like you know the final result. The number is going to be 5 because you started with 5. Or it's going to be 4 because the last number in the list is going to be 4 because you just look at the input and derive what the last number is going to be. But here, you have to actually start at zeros, so you have to do the thing, you have to do the operation that many times. Yeah. So I can't do it that way. I couldn't possibly do it that way because when I get to the base case here, the last thing that I tack onto the end, the first thing in the list, right? Uh, has to be the base case. And in fact, that's exactly what I was hallucinating, right? Because I saw the list was in ascending order, so I was thinking that it would recurse and then add one, but no, of course, it just it has enough information to recurse on the way down, but here you don't. So if I knew what the 10th prime was, and from that I could derive the 9th prime and so on, then I could do that. And but here I have to like recurse all the way down to 0 and then build, and then in the return stack, then every time I return something, I tack the result on. So the x gets, the value gets passed down, 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 and then at the very bottom, I append it, and then append it, and build back up, go back up the call stack. Okay, this, again, I was going to try and prove this. I think it's possible. I'd like to learn how to do this better, but I don't want to do this right now. All right, so I'm just going to do this and save this, and then I'm going to this was a little rough, but so the next thing now what I want to do, first I'm going to check my code in, but second I want to take this, and now I want to rewrite this prime sieve in terms of all these things. So I'm going to use this prime generator here to make what I'm calling rake sieve. So right now the main operation, this thing, like it generates all these primes, but it doesn't, and it's using the idea of a rake, but I haven't, like when I wrote this, I hadn't formalized the idea of a rake yet. So let's try that. So first, check in my code. And by the way, this is all up on Google. Yeah, on Google. On github.com tangent storm. Tangent storm. It's called tree sieve right at the moment. Because I'm working on making, the original idea was to have trees of these things, trees of where the, doesn't matter. There's some explanation of it here. I was going to use it, as a demonstration for an idea about validating classes of numbers. Like, there's a story for another day. Do the same partition operation, and you can, like the Collatz conjecture. When you trace the tree backwards, you start with a number, and if it's even, you divide it by 2, and if it's odd, you multiply it by 3 and add 1, and so that makes a tree if you work backwards. So you partition, based on by feeding the input 2n plus 1 and 2n plus 0 into those two. I don't even know what I'm talking about. Anyway, whatever. I was thinking about using this to make a different kind of sieve, not a prime sieve, and but then I got sidetracked as usual. And in a couple weeks, there's going to be a video about this that makes a whole lot more sense. It's all summarized and compact and what. When you get me live, you get a stream of consciousness. Whatever. I think this is already in one of the other files. I think it's in. Okay, hang on. Yeah, it was already in here, and I just moved it to prime sieve, right? So then sieve is also prime. No prime factors included. So this can just be empty. This I can just revert. It's been sitting in my working copy for a while because I was going to move it to the sieve thing, but now I came up with the idea of a rake and whatnot. So the rake being the list of arithmetic sequences that all share the same. This sort of list of arithmetic sequences that share the same delta. Not terribly well illustrated by this, but this is like 8 different lines, very big dots that are all superimposed on each other. That's a picture of 8 sequences. Okay. All right, so this was file I was just working in was prime gen. And the difference that I did on that file is what? Okay, so I moved all that stuff there. Oh, I did 3, so I moved a bunch of stuff and I added f pound prime. Okay, so how about we call that cleaning up prime gen, and I move. It's really 2 different commits, ought to be 2 different commits. Move prime gen, move sieve stuff to prime sieve, and add primes function. Primes and fval. And what has changed here? I cleaned up a comment. I'll just go ahead and. Yeah, it's not. Right, we'll commit that, and then we'll call this next one minor cleanups and get those things. These hit and push. Okay, that annoys me. Complaining that like I haven't saved everything. Save everything. File. What annoys me is that like it's possible, yeah. So now prime, yeah. See, like now this, I've got uncommitted changes down here. I don't know if I necessarily. I'll keep. Saying that I've defined it twice because the imports are out of. I think that's good. So now I can commit and push this. And then I'm going to call this minor cleanups, and this is a minor cleanup. Double check that. Over here. Yeah, so this was like a copy and paste, so I replaced it with sorry. This I had the wrong word in here. And then this was a minor cleanup. Okay. How long have I been at this? 3 hours almost. Half of it was not productive at all, just me rambling. Okay. All right, so More than half, I'm sure. Playing around with sieves for composing music. Interesting. I would be very interested to hear what that was about. Okay. And you're welcome. Breaks it. What's mad about here? Probably just because. Okay, so maybe wrong here. Port prime gen. Why is this? Why is this not? We have to say open prime gen. But I didn't use a namespace. All right. It looked like that fixed that, but it didn't, right? Non-identifier C, so that's not it. Why is it red here? Like C is defined here. I'm not sure why that's not. Unknown identifier C. When this was here, it had no problem with that. And my understanding, like as far as I can tell, was it because I moved it inside of this? No. Gen C. There's no namespace here. As far as I can tell, there are no like you have to actually use like I was getting an error earlier because I had a file, like two files imported this, and I imported both of those files, and it said hey, you can't do that because nat prime is already defined. So that tells me there's just one global namespace until you explicitly like import doesn't create a namespace unless you explicitly say use the word namespace, right? So that means you shouldn't have to say open prime gen, but then like it knows what a prime gen is. It knows that it has C. Like what if I say check prime gen? I need to no. Okay, check. Oh, it doesn't know what it is. Unknown identifier CH prime gen. Like, what is that? Is lean dead? Is it messed up? Ah, see now it works. Yeah, lean was messed up. But why do I suddenly have to have this? If I put this line right underneath prime gen, I say is it use? No. Open prime gen, right? And that fixed it. And if I take this, then it breaks. Okay, so I need this word, open prime gen. Oh, I see. So prime gen is a class is a namespace. So prime gen is in the top level namespace, but I sought to open prime gen to use it. Now it's going to be mad and tell me I have to restart this file because I saved this file. So let's say open prime gen. Oops. Open prime gen. Okay, and then this should no longer. Look at that. It's getting screwed up. It says prime gen PE, as if it were like catching me in the middle of typing something. Like maybe that PE right there, an open or something. Now it works. I'm gonna restart the Lean server, and that's gonna take like a couple seconds, I think. So my OBS just crashed. Yeah, my OBS just crashed. So I'm gonna see if it says I'm streaming now. It says I'm connected again. It just like when I restarted Lean, OBS crashed. I don't I don't know what the cause and effect was there, but I'm gonna check on YouTube to see if I am still streaming. It says I'm live, and it shows me with this screen here, so I guess I'm back. Okay. All right, so sorry about that. No idea. I guess I'm not really sorry because I didn't do it. But okay, a bit of excitement there. So maybe I actually clicked. No, it would have asked. It would have prompted me to click save it. Whatever. No idea. Maybe my computer is full of bugs. There's a literal bug crawling around in it. Okay. All right. So we want to prove all of this here is kind of junk. Like these are the things I wanted to in general say about a prime sieve. Right. So that basically a prime sieve is a generator. So maybe we should call this whatever. I'm not sure yet. Like these are the proofs of it. I don't really know how to express this idea yet. The idea is that there's some characteristic of an algorithm that makes it a sieve, right? And you can look at the algorithm and say, okay, that's a prime sieve and that's not a prime sieve. Like this is, to me, this is not a prime sieve because what it's doing is there's maybe far too many definitions here to make it clear what's actually happening. But basically, it's doing a nat find. So given the fact that we know a prime exists greater than C because of this proof that there are an infinite number of primes, then we can find the next prime and return a prime greater than C. We can return one. So this is a type that given that it's a dependent, it's a type that depends on this parameter C, and it is the type of natural numbers, the subtype of natural numbers, such that that this proposition holds, that C is greater than P. So this proposition is a type. Prop is a type that is dependent on these two things. So the natural number, it's a natural prime, nat prime, right? That is less than or greater than C. So that's prime GT. Or rather, this is a proposition that is true when P has that is a prime and it is greater than C. And then we say, okay, this is decidable. And then we also show that such a thing exists. And then if it's decidable and it exists, then NatFind will find it for you, or at least try to find it for you. And it does that, as far as I know, by just counting up from 0 and seeing and running this thing. And maybe it's a little smarter than that. I haven't really dug into the code. And if yeah, like, what is it? So it's doing some magic here, but looks like it has some property that is true of that number, and then for all m less than n, not this number, so it has a cutoff, I guess. Yeah. I don't know what this is doing. I'm just picking out little pieces of it. That's probably short for induction hypothesis. So, oh, I don't know. Lower bound property, maybe. M is n plus 1, and for all k less than or equal to n, not pk. So given m, n is the lower bound property. Well-formed lower or well-founded lower bound property. I don't remember what well-founded means. I don't know what it means. Are accessible within R. Does not okay, so you can't just go forever like a you can subtract forever, but naturals numbers start have an end. They have one end is 0. I don't really know, but I suspect that if you decoded this, it's a for loop, right? Like maybe it's a little bit smarter to figure out what that lower bound is. Maybe it looks in there to find a lower bound and can deduce a lower bound. Yeah, like here, if you have this, I don't know. I would have to study this for a lot longer to understand what this is saying. This is IH again. It's got to be induction hypothesis. What else could it be? I mean, it could be anything, I guess. Oh, it's just a parameter. If M has the property, so P is some predicate or property, prop, and if M has the property, PM is the hypothesis. Like this is saying if PM, and then PM is this, right? So if this property is true, if we know that from the context, then return some structure, whatever we're returning. I don't know what the type of this is. It's returning this. So n would be m is being mapped to n, and then lost it. And then this is PM, and then no wait. Oh, this is AL, so this is the all. AL for all, probably. So in brackets there, I can't hear where the cursor is pointing. This stuff can return. Oh, I see. Yeah, it's actually returning this, right? So this is the same thing. So these three things are the elements of that. So M is mapping to N, PM is mapping to this, and AL is mapping to this. So that is the return type of find X. which I bet are those three things. So the spec, the min, and the min prime are the proof that min prime is that m does satisfy the. So this is min, right? For all m less than n, that the property does not hold, and therefore n is the minimal number. And this is that it's true. So this is okay. So it returns three things. It returns the thing that find returns n. Find spec returns the proof pn, and find min returns this, right? So in order to return that, oh, I see. So well-founded is already some other function that is taking these functions and doing magic stuff. So the actual work is being done in well-founded fix, which is in fix f, which is not something this knows where it is, right? But maybe when it rescans this file, it'll. No? I don't know. This is part of lean init. So I mean, this should. It's not this word prelude wipes out every definition you have, I think. I'm not clear why that. I don't know what this means. Did not I'm in uncharted territory here. All right, whatever. So my thought is that, I mean, in general, fix looks for a fix point, maybe. I don't know. So keep supplying things until it stops changing. So probably some kind of reduction rule. I don't know. No idea. It says, yeah. I don't know. A lot of this is not documented well. I don't know what this align means either. Oh, math port thing. It's a tool for upgrading from Lean 3, where they changed the naming convention to like use uppercase letters for these things. Like 2 years ago, I tried to volunteer to do a little work to upgrade some stuff, and I just didn't have the time and energy to get into it, and it was required more expertise than I had to help with the translation. All right, I'm off track here. All right, so I want to make a prime sieve. I learned, what did I learn? That to make this squiggly line go away under the C, we have to say open prime gen. I guess I knew, but now brought to my attention here. All right, what now? So this is a generic thing. Like I have, okay, hang on. So I have two actual prime sieves right here. I have two prime generators right here. One is a simple generator, and I have one prime sieve, which is in main. And async or async prime sieve has the following thing. It has a list of primes, async. It's a arithmetic sequence, so async. A prime sieve based on arithmetic sequences. It has all the primes we found so far, current primorial, next prime, list of sequences. And again, it's just partitioning, starting with the line or the sequence 0 plus 1n, and just partitioning to 2, then 3, then 5. It finds the prime and then partitions in that many pieces, wipes out all the arithmetic sequences that produce multiples of that prime. And so you wind up with like 2 times 3 times 5 times 7 times 11 times 13 and so on, just like a huge number of lines, hence the name rake over here. But here, what it does, it's not arranged in an object called a rake. What the rake brings to the table is two things over this. So I'm going to kind of compare them side by side because the rake is like the 2.0 version, you know, or really rake map is. So the idea is that we have an A sequence over here, a list of A sequences. And over here, we have a list of D sequences, which are just an A sequence where the type, where the delta term, the slope, is, you know, it's k plus d times n, right? And the d is hard coded into the type, and so we have a proof that they're all the same. They have the same slope, right? So that defines the type, and then the rake contains that number d and the list of sequences of that type, right, with all the same slope. So you cannot put, if d is 10 or 5 or whatever, if d is 5, you can't put a sequence in here where the slope is 7 or anything like that. It has to be 5. You cannot construct a rake like this. You cannot construct this, an instance of this structure. You cannot construct one of these things, a value of this type, if that's not true. Type checker won't let you do that. And then you also have to prove that the list is sorted and the size of the list is greater than 0. So you have to have something in the set. I guess, yeah, I could get by without this, but I don't need, you know, what's the point of filtering an empty set? Okay, so again, to compare, I guess the comparison ends kind of there because now we have step and there is no step over here. So the idea would be to now rewrite this in terms of a rake. But maybe well, okay, so there is more to the comparison here. Like what this is implicitly doing, and this has no proofs attached to it, right? So what the rake brings to the table is that it has proofs. That's what I was trying to say. Or it will have proofs. Right? And specifically the rake. So the rake itself is just a list of parallel, parallel arithmetic sequences that are sorted in order. You know, so that, you know, this top data in this little collection is always less than this over here, because we took a straight line and we like partitioned it. So like all the dots that were like, we like took a bunch of dots that were over here, and the first 1, 2, 3, 4, 5 or whatever all went into one little line right over here, and then the next one they're in a little line over here because they're moving to a different polynomial, and the polynomials are all stacked up over the integers, right? Right. Again, an animation would make this much clearer, but kind of get the idea from this. And so it's a partitioning, and I don't really prove that it's a partitioning yet. Maybe I don't need to. I don't know. I kind of think I do, but we'll see. Meaning proving that if a number is in one of the sequences, it's not in any other sequence. The idea of a partition, or the property that I would prove about the partition. That is true, but it's not proven. what I did prove was that it exists in some sequence. That if the rake as a whole has a value in it, then that value is in there must be a sequence that contains that value or that generates that value. What I have not proven is that there's exactly one of those. I suspect I'll need that proof stuff later on, but we'll see. So here what we're doing is we're just saying, okay, I know I'm going back and forth. I'm trying to like narrow the gap between these two ideas here. The unproven, I guess you could call this informal. Like even though it's written in Lean, there's no formal proof of anything except this field right here, the next prime, which is called C, C in the prime generator that we were just looking at for current prime. But here it's called the next prime, and that next prime is always prime. And this is the assertion. It's the type of NP is prime, is n prime, right? Which is just a subset of. I define this in prime gen. It's the nats where nat prime is true. So the subtype of nat where nat prime is true. And so I don't have to have this. If I didn't have this, I would just be using a natural number, and then I could just say, I could get rid of this proof here. Oops. I don't know why that didn't work. Expected type must be an inductive type with only one constructor. That's exactly what this is. Oh no, NP is a nat, so I don't even need the little brackets. Sorry. Nat is an inductive type with two constructors. It has a 0 and it has a suck of something, a suck of a nat, successor of a nat. So you can't use the brackets to create a nat. And then, so, right. But as soon as I say n prime, right, and you can see like it broke about a lot of things. So n prime is actually a wrapper for nat, where you get the value from this dot val kind of thing. So if I turn this back to n prime, now the type is changed, and we have to access that thing. So it'd be like val equals 2, and then I guess prop is the other property is the proof that nat prime equals 2, and you can say it like that. But for these things, it's obvious what the what the fields are, and so you just say 2, and you don't have to say property. You don't have to say that. That's syntactic sugar. All right. Because that's different. So okay, so that's it's a 2 with the proof that it's a nat prime, and that's making it an n prime. And so then when I did this, like I already calculated NP, and I had to prove that NP is prime here. So in each step, I had to prove, and I don't know how to prove that. That's the question, right? That's the entire goal of this. That's the reason for creating this whole giant file, right? Like this is a working prime sieve in like however many lines this is. A little extra to print it out, and there was a little extra to define what a really I needed this line and maybe term here. So like it was it was a very small amount of code, and then now I'm like theory building all around this tiny bit of code, right? And so I have this that uses that ASEQ type, arithmetic sequence type, and okay, you can apply the formula to a number and get back the result. You get the nth term. You give it a natural number, it gives you back the term in the sequence. You can compose it, right? So you can feed it another sequence, and then you can say, well, okay, this would be the composition of those two sequences is a sequence. And then you can generate some terms. So you just feed it in list range n, right? And that's about it. Okay. Why do I have this open? 1,000 problems. I only need one. I want this over here. This is, you know, Visual Studio Code has this nice environment for Lean. And it's the official environment. But I was looking at the other file, right? I wish this were like a doc string and you could like test this, like these comments or whatever, that they actually prove that. I guess I could make some kind of, like, I don't know how, it wouldn't surprise me if there were. Anyway, so you can see the terms of ID. So IDS is just make this sequence, you know, with k equals 0 when d equals 1. So 0 plus 1 times d, or d time 0 with 1 times n is the sequence. 0 plus 2 times n is the evens. 1 plus 2 times n is the odds, and it all works. Right, but like this is unnecessary. This is like I needed this as the initial start of the sieve, but I don't even know if I use that over here. Main. Yeah, I just said it starts with, yeah, I don't even use IDs. I start with with 2 plus 1x, 2 plus 1n. That gets rid of 0 and 1, and then just, you know, it's this thing right here, right? 2 on this axis, 0 on this axis, and just goes. That's that sequence right there. And then you just repeatedly look at the first item in the sequence. Which is list minimum. Give you the next prime. Returns the smallest item of that list. Oh, because what it's doing is, so you can apply the series to the number 0 and get back a result. And this was the case. So I started with 2x plus 1. Before that, it was just 0x plus 1. And so I had this this line right here. But I don't need that anymore because I'm starting with 2x plus 1, so I'm just going to get rid of that. So for each series, just give me the first term in the series as 0. And then get that series, right, out of SS, the list of sequences. Okay. Wait, what? What is the get for? Oh, because it's option, because there might not be a minimum. Right, because you might not, if it is not empty, right? So if the list is empty, so you have to fix that. Okay. So it's just wrapped in an option type. Turns option A, option alpha. Okay. So we have, at each step we take a structure like this and we say we found a new prime, so we take the next prime and add it to the list of primes. That's what this says. S0 is the sieve at that starting sieve at that step, right? And then we're going to map it to this sieve right here. So we're returning a arithmetic sequence prime sieve, using this. And this, I bet you could say decide here. Why decide? Why not? The point is that you have to prove that NP is prime. And so NP, the type of NP is what? We can do it like this by saying right here in, let's see, proof. Let plug, okay? So let proof, wow, proof is equal to, and then we'll say sorry. We'll put this here. And this is proof that NP is prime. That's sorry. But if we go right here, well, at prime, come on, prime NP. Oh, because I don't have the word by here, that's why. I was trying to figure out why the context didn't, or on the right here, it's supposed to tell me what I'm trying to prove, and it's supposed to tell me that it's not prime. Yeah, right. I didn't, and then when I explicitly put this here, it still didn't say that. So it's because I had the word sorry, but no, I didn't have the word by. So that now it's going to tell me what I have to prove. Or you can put this here. No, it's not. So I have to prove that not, and I think I can say I decide, right? Apply decide, and I have to say, how about ASOP? It failed to prove, okay. Well, I mean, this is the point. It doesn't know that it's prime. But given that it's... Surely there is something in here that says not prime dot decide. Right. Like, there's got to be some function that looks at a thing and checks if it's prime or not. And if it is, produces a proof. How about, look here, let's, I don't have a lot of luck with this, but what if I say, I don't know how to use it yet. Oh, we'll say, given a nat, I'm going to say like option nat prime. Something like that. Is prime? That is prime, maybe? Nat prime. That's probably what what do we call it, right? Side, but just is prime. Hmm. Can I even do this? I feel like I can. Like, I'm not sure if I can do this or not because like it's a type, but I want to construct that type at runtime. The type being the proof that it's decidable. I don't know if I can do that. I don't even know if that's possible. Oh, but hang on. How is not prime 3 defined? I see what the problem is. I don't see how to fix it. The problem is that this happens at compile time. Whereas I don't know what this is until runtime. So I cannot stick this in the it's a type, right? But there has to be something that gives you like an option or fails if it isn't. Maybe there does not have to be such a thing. Maybe you just can't do this. Um, I would. Not right now. So you guys go. Have a good time. I'll see you in a little while. They're going to the park. Hmm. I'm looking for something that has a nat on the left and prime on the right, but it has to have a colon or a arrow in between. I don't. I feel like this is possible, but like it has to. It would have to return. It'd be a function. By norm num, which is much faster, but that doesn't give me. Again, it's proof, but I. What am I trying to say? It has to be something that you do at runtime, right? So it has to be a function that. I think you just can't do this. But you ought to be able to. Probably what was actually the case is that it just is not. It's either not implemented or it's in the lean for initial code. Like I think there's something about primes. I don't. Maybe not. Why would there be something in that's outside of mathlib, right? Like why would. Hmm. I could have sworn that I had like every lean package got stuck under this directory. Like if I just say like, ah, yeah, this doesn't matter. If I wrote a function, it ought to be possible to write a function that returns this type. And it would just. Like this is not important, right? Like I kind of want to just do it just to understand from my own understanding how does this work. So is prime going to take a nat and it's going to return a proposition, right? No, it's going to return option nat prime n. Is that even reasonable to say? Nat prime n equals none, right? What does that mean? Given an n, I mean, you could do this, but this wouldn't be sound, right? You can't. You'd have to say, I'm trying to get it. Say nat prime, and you can't construct this type. I mean, you can say this. Like I've hit like the wall in my understanding of. So this is not. So you can give this number. So we say eval is prime 4. Oh, okay. So we're only able to go from a prop to a boolean to a value if it's decidable. So then instance, aha. We're going to say if is prime np, then we have to say option, right? So say proof else none. So it's not a. Is there a panic? What do we do with panic? How can we have a panic? Option panic. I see. Right. So panic returns none. That's how it works. So it returns none, but also somehow. Actually, somebody's trying to call me on their phone. What's that? I'll call him back in a little while. And then yeah. Guess we have to match on this. And if it's S, then we do this. And no more primes. Panic, no more primes. What did this say originally? I think I screwed something up. Oh, print SVN. Wait, you can say I was trying to do this earlier and it wouldn't let me. Yeah, maybe it has to be a maybe mute has to be inside of IO. Oh. All right, so let's call this SV prime. Oh, I see. What's it mad about? There you go. So everything still works. And now I don't have a proof that it works, but it's more like, let's call this like runtime check. Okay, so the answer is you can do that. And in order to get a prop at runtime, it has to be decidable. Okay. Interesting. Did I not return this here? Like, I can't. If I tried to do this and just panic if in the else case. Yeah, it has to have some kind of wrapper here. Maybe there's an error type or something like that, but what I was going to say earlier is that I mean, you can. Wait. Not is prime, but nat prime or right. Wait, is that because this exists? Do I need that? Maybe I don't need. I don't need that because it's already decidable. Oh, so the whole thing I was looking for was this. I was looking for something that took a nat and returned a nat prime, and that's what nat prime does, right? It returns. Oh, okay, now I'm confused. Okay, so this is something in type theory I don't understand. I could go down the rabbit hole all day with this. But somehow I'm able to evaluate this and evaluate it as a Boolean, and that's because I know that this is decidable. Somewhere in here it says decidable, and it is prime P, right? Wait, can you just say, wait, my simple sieve over here, can I just say, can I just say not, can I just say eval not dot find not prime, not dot prime? Oh, so some kind of like some kind of thing that a prime exists. Not prime dot x. Not prime 3, it's prime 3, right? Not primes exist. This prime, this p, at prime p, right? You guys should be able to find that. Oh, you would think that something like that would work, but exact, right? This should is exists the prime that I'm just babbling here, right? All right, so exists a prime. Okay, so have P phi, which is that nat prime 5 by norm num works, but it didn't work. There we go. That didn't work. By nat prime 5. Apply nat prime 5. There we go. All right, so now we have a proof that the primes exist. H specs, right? It's right there. Why can't you see it? I could just do it. Again, wasting time, but I mean, it's not entirely wasting time here because I'm learning something, but I don't know what I'm learning yet. I think I passed that in right here, and that works. Why doesn't that work? Well, maybe because prime is misspelled. We'll have H. Why can't I find H? I don't get that. Expected type exists n such that nat prime n. This, oh, because it's an maybe prime n. I still can't find it. Is it because I'm trying to apply this to something? No. Not find H. Hmm. Oh, hang on. What was I doing? I did this. I see. I was expecting. First of all, I had them in the wrong order from what if I thought that was true. So like I'm trying to pass in this. Hang on. It doesn't work because this is an implicit argument. But if I say this, then I have to show that nat prime is citable. No, it's not citable prime. Yeah. Okay, so now I can do it. So H is a proof that prime H prime some prime exists, and it'll go looking for one. And the proof is just that 5 exists, but it's going to find 2 because it's the first one that exists. So what did I learn from that? I learned, well, first of all, I learned this syntax, right? That I'd seen before. This is the first time I ever used it. You say nat.find, you only want to have to give it H. Oh, right, H. I renamed it. Some prime exists, it's going to find it. But what I was imagining was that you had to pass it nat prime, and you can, but if you want to do that, you have to use this at symbol, and then you also have to pass in the other implicit parameters, which are that. So here's the prop, which is nat dot prime takes a number n and returns the proposition, returns the proof that it's prime, and it has to be decidable. And H is the proof that some number exists, and it will find one. That's what find does. Oh, I see. And then here in my sieve, I'm basically doing the same thing, but I'm passing in. I return 2 things, right? Return that the prime exists, return find and the spec, the proof. Prime GT being a, yeah, so T is a nat and it's a prime greater than, and prime greater than is a proposition that, right, so this proposition has to be shown to be decidable. Do I even need that? Yep, I need that. And I have to show a prime exists, right? Because I changed it from just nat prime. So the question I was going to get at is could I just like somehow use nat find with some prime exists? And I think that like this is how much work it takes to make that happen. Okay. Well, I've been at this for a long time now. And I think, I had actually intended to like work on this, but I did something here. Like I did, this is now, I can now say this is a, well, I can't say it's correct. I believe it's correct, but now I can say that if it's not correct, it'll crash. It'll panic. That's progress. So if it runs, it's correct. Well, is it? Because what am I trying to say? If it's possible right now that this produces primes I mean, I can see that it's worked correctly, but it's possible that somewhere down the line it skips a prime, right? And it produces the prime after that. It doesn't. Like, I believe it doesn't, but I haven't proven that it doesn't. Right? So I'm like, well over 99% sure this is correct. The code is correct. Like it's obviously correct, but that's not a proof, right? The computer doesn't know it's correct. But here, now it knows it's gonna fail if it's not correct. That's proper. All right, so I learned that. So let's record that. Different here. That one extra blank line at the top, is that different? Oh, the word prime gen. So we'll say main runtime primality check. Yeah, so it's not so it's this color yellow because it's changed in Git. But once I commit it, it used to be this color yellow, this kind of goldish color, because it had the word sorry in here. But now I don't need that. I have a runtime check. And so this is like, I mean, technically this is a formally validated prime sieve, but it's not what I'm looking for, right? I do want to wrap this up soon, but maybe I'll go a little bit further. Lemmas. Oh, just lemmas about primes or whatever, or about nats. So this is not being used yet. That's why the main is not bold, yellow or whatever. So these are all facts about prime sieves. And again, I don't know if I finished the thought earlier, but like the hard to point at something and say this makes it a sieve and this makes it not a sieve. Like it's easy to look at the algorithm as a human and say, okay, well, this is just doing trial division, which is what led to that tangent down on nat find, which is just, as far as I can tell, doing trial division in a for loop or whatever to find the minimal prime, and in this case, the minimal prime greater than the previous prime. But a sieve somehow represents this set that, the set of known primes, and more likely the set of remaining numbers that are not, like things that have not been crossed out yet or removed from the set, right? And if you can represent this set, there's two ways of saying the same thing. If you can represent this set R, and C is in R, because C is min of R, right? That implies that C is in R. Then you take that C out of that and you put it in S, and then you remove all the multiples of, right? So S is the set of primes that are less than C, right? Less than C of X, X being the state of the sieve, right? So C is the current prime in this sieve. There, for every current prime, there's a set of primes less than that. So this is a dependent type based on C, on the state of the sieve. X is the sieve, C of X. And there's some known primes. And then there's this set, which is all the primes that are all the numbers that are co-primed to those. So all the numbers greater than 2 that are co-primed. So that's all the powers, all the multiples of 2 and 3 and 5 and, you know, all those filtered out when C is like 7 or whatever. 1 is filtered out by this clause. Have I ever actually proven that? Okay, so this says C is R trivial from R min. C is in S prime, which means after we apply next, then we've moved C over from R to the list of primes, and then we have some new C, and then we have C is greater than, or C prime is greater than C, so the next C is greater than C, and somewhere is this, and then this is the thing. Oh, and I was trying to prove this. I was trying to prove this step right here. Do I have prime sieve spec? Class prime sieve. I'm going to just call this. It's all the same. All right, so then here, move this up. So a prime sieve is a prime gen that uses a sieve to generate primes. In practice, this means, comma, this means that it somehow models the set of natural numbers greater than 1 that are co-primed to a list of known primes. And then repeatedly obtains the minimum of the set as the next prime, and or identifies the minimal, obtains the minimum of the set as I don't like the way that's worded, but whatever. Eliminates multiples of the new prime. And so I'm saying that this is kind of like what I did for rake map over in the other file, right? Is this the same file? What is this? This is the diff of the file I'm looking at right now. In not rake sieve, in rake and rake map, I have this notion. What was I going to say? Basically, okay, the rake map wraps a rake is what I was getting at. Rake map has a rake and this bijection. Prime sieve spec has a gen which is type A, and we call it PG as an A. I think I even did this. I just called it X here. Oops. I was trying to make multiple cursors. That didn't work. Is it Alt Shift? Yeah. But I did need a not Alt Shift. Shift Alt. Control Shift Alt? Is that? Yeah, it's Control Shift Alt. Control Shift Alt. One space. Okay. And then the idea is that this. What is that? Prime sieve, pro spec, prime sieve spec. I must have searched and replaced something. Prime sieve A. No. That. I need this. Yeah, because I'm not talking about it. I think this should be a class. That's part of my problem. This should be a class. That is exactly why I had that like that before. Because I think these have to be passed in. What I had before. And then we would call this prime sieve A alpha. What's wrong with this? Imports are out of date. Why is that a problem? I know it. Why can't I do that? That's type. Why can I have why doesn't it like that? Spell it weird. Doesn't matter. It's not clear to me at all why I can't put the I can't say this. What? This is a class. A. Oh, because this is a prop, right? It's not. Have to be implicit. The brackets are implicit, but like one is handled by the type checker and one is like handled by the say elaborator. But I do not understand why I can't put it this term here. Term has type. Function expected at prime sieve. Is it because of this? What is different? Here, oh, I see. Here, okay. The argument is in parens as opposed to curly braces. So, okay, so how I would have fixed that by putting an @ sign here. Yes, that would have fixed it. Okay. So without the @ sign, you have to, can't, the @ sign allows you to use these explicit parameters. Use these implicit parameters explicitly. What was there before? You, right? Type in the current universe. Okay. That was the difference. The difference is I had curly braces before. I don't have them. Now I don't think I need this. I think this is implied. Oh, okay, no, you have to have it. Interesting. So what does that say? That's going to tell me that failed to synthesize prime gen A. So it's saying that you have to have a proof that whatever. Okay. Interesting. Okay, and then so now what is it? So for all x of a, yeah, I don't even know what that is. I don't even know what this term is. Okay. So we want to say, oh, I don't even need this. So given these types, these in, oh, okay. I guess it really doesn't matter whether that's implicit or not or whatever. But now, given one of these prime generators that I'm asserting is a sieve, and the next state of that sieve, and the assertion that x prime is is that next state. So two prime sieves, and one is the next of the other. Then I want to prove that for all, I want to prove that C prime. Let's define C prime. def c next. But how do you compose those two things? Oh, I don't think you can do function composition now. Prime sieve alpha. I don't know what why can't I do that? Oh, because it's a prime. It's on prime gen. Prime gen a, and the type is going to be nat, right? Nat n prime. No. Okay, I see what it is. Yeah, this is a little verbose. You have to say that you want an a, or you want an x that is an a, and then a is a prime gen, and it returns an n prime. And what's wrong with that now? Fun x has type something to n prime, but is expected to have n prime type. Oh, because x is already being passed in, so I don't need this over here. That. Okay. So then I can just put this in prime gen. We say open prime gen, and then the C works here. And I think I don't need to say open again up here now. Maybe I do. But we have to restart the file to find out. Oh, we do. Okay, so on in each file, we need the word open. Otherwise, this little thing gets squiggly. Okay, and if I, just to double check, I comment that out, it gets squiggly again. Oh. Let's see if it's not responding. Yeah, it does get squiggly again. Squiggly again. All right, so now instead of saying C and X prime and all this stuff, we're just going to say for X of this, C prime of val, or C prime X val. Wrong here. Unexpected token and, there is no and there. I mean, there's an and on the next line. That, somehow that got screwed up. Do I need this? New C, whatever H new C is, where's that? This, okay. I wanted to have, I was thinking you'd have to prove this, but maybe you don't. I think I don't need this anymore. Yeah, because I implemented the COE of NAT, coerce to an N prime, or coerce an N prime to a NAT. So I don't have to say .val everywhere. And I did that refactoring earlier, or days ago, but this was all commented out. So I wonder how, I think function, yeah, so now I don't need that. So C of X and C prime of X are, so we could say that now. C of X less than P and that. So I'm going to put this comment together. We have a new bigger prime, we have a newer, we have a newer prime, a bigger prime, new bigger prime, and there is no prime between. I'm going to put this all in one line. And I lost a comma there. Yeah, I lost that comma. So this says that C prime of X is greater than C of X, because we have a new prime. Oh, let's put that part in parentheses. And there is no prime, there's no N prime between them, not prime between them. Such that C of X, right, the C of X is less than the prime, and the prime is less than C of X. So there's no prime between these two things. And so let's also make an S prime because we need that, and probably R prime. Let's just go ahead and make all of them. Oh, but okay, but hang on. S is a concept about prime sieves. It's not in that world. So say we have to do it here after prime sieve is defined, and do that same thing, but just now we define it for S and R. S prime and R prime are going to be S prime is set N prime. Would be S of next X. R, and this is a set of naturals. Yeah. I'm just giving like syntax to this. And I was just thinking, maybe I don't want to repeat this over and over again. I could say, I could say something like section. I thought you had to give a section a name. I guess you don't. You can say variable XA. But I think by doing it in here, I've broken the inside the section. I've broken the name. Yeah, so now you can say that. But now I can't see it. Oh, can I? Okay, so it does see it. So the section only isn't a name. It's only a namespace for the variables. That's kind of nice. So R prime. Wait, what did this used to say? Oh, HR. So there's a hypothesis called R somewhere. Called HR somewhere. Oh, okay. There used to be a hypothesis called HR. Now it doesn't exist. So that's why that's broken. Right. So unknown identity or by ESA. This is gonna. So I have to prove this. So CPKS. I think that's actually this right here. Co-prime to some known primes. CPKS. This may be complete garbage. Have CPKS. Oh no. So this is the proposition I'm trying to. Is that used anywhere else? Because I think I'm going to inline it. It's used several places. Well, it's used twice, but only to. Yeah, only to get this line. So. So this is what I actually want to say. Have. Maybe let's look and see what I'm trying to prove. I'm trying to prove this statement. And the main argument is an and, so we use and intro, give the case, and we get H nu C, which is I guess this, right? C prime is greater than C. Because now this is C prime C. It would be nice, like, to have. This is exactly where you'd want to have, like in J, you can express this as C prime greater than C, and you don't have to pass that X in. It's called a fork. Like you can just write exactly this. It's called a monadic fork, where the argument is passing on both sides. And like all of these, like this is right. The X val. Oh, right. Why I can't use? I have to use val there. Like this one. And hey, Hank, what broke? Hmm. Why can't I say that? Hmm. I guess because these are forward references. I wish you could say that. That would be. You could make that a macro or something. Introduce notation. I don't know. Or another thing I was thinking is that like the forward referencing is one reason that in this type, in the rake type, I have structure rake, and then only later do I take that same thing and just connect it with something else. And that's because I didn't like I wanted to have all this stuff like predefined and like unfoldable so that I can refer to it and say take this apart or whatever in order to do the proofs. I may have refactored things, so I don't need that anymore. I'm not sure, but like it would be nice to have, to be able to say S prime here. But whatever. I can say C prime because it's already defined for at the prime gen level, but R and S are not. They only exist here. Or actually, they exist up here. Oh, wait a minute. Oh, these do exist here. You don't. It doesn't have to be a prime sieve. It's all. It's all. These things are all defined up here in terms of prime gen, right? So if we say section accessors, then I can move. And I say end accessors. Then I can move this up here. Then I can remove these arguments here and these arguments here. This is like an old way of formulating R. I don't know that I need it. RS. Can I see references? I know references. RS. Okay, so that was. But I think that's old stuff I don't really need. So RS is a set of nat relative to the current prime. Whereas here that it's not tied to the X set at all. So this is a different way of formulating that. Another way to formulate R without reference to a prime gen. It's almost exactly the same, except this one uses S, which uses C, right? Not necessary, it just makes it look easier, just easier to see. Okay, right, so I was able to strip out all this. That's cleaner a little now. I don't need this word here. Section just gives you like a local variable here. Okay. Really, I don't need this until I use it, right? Which is down here somewhere. FRS, all this stuff. So this is garbage. That's like the bottom of the file. Probably don't need this stuff. All right, I'm going to move this into the section and then I can get rid of this here. Do I want to do that? Yeah, probably. Does that work? What happened there? Something broke. What happened? Why did that break? What changed? I added A as a type in the universe. Is that right? Oh, maybe. Okay, that was fine. Because I had two copies of that word up there and it broke that. That broke. Is it because this was defined first? Yes. So if I define it explicitly with the with friends breaks, I make it implicit in the. I don't know why that's the case. Okay, anyway, but now I can move this inside. And I guess maybe they don't indent this as the. When I go to nat prime, I think that had a section at the top. Yeah, they don't indent. But I'm going to indent. Do I? Do I want to? All right, so now we know that alpha and this are the same. And we've defined a variable already, so we have that there as an explicit variable, I guess. And we don't need this because we've introduced a new type A here, and if we get, or alpha here, and if we get rid of this, I think this just works, right? We just get rid of all that. All right. Oh, but now this broke. Okay. Why? I'm still in this section. Oh, can I say prime sieve here? Probably not, because it's not defined yet, right? But then after I do this, we'll just put it here. Do this, and no. Let me say variable. I guess we have to start over now. All right, so end section. Not this. We have to start over because here, like, we're using the. I'm not sure. I'm guessing that because we're using this variable now, and it wasn't a prime sieve, and we've used it like implicitly in here. Now it is a prime sieve, so oh, okay. Well, it let me define that, but it didn't. Okay, so I need to actually have that. Is that right? Failed to synthesize prime gen of type U. Used. Sometimes I just, I need to just try a bunch of things. Okay, so I fixed something like this earlier, and the fix was replacing some commas with with some parentheses with curly braces. This wasn't necessary. Everything inside that section should not need this. It doesn't. It's able to see what X is. It knows exactly what X is because of this. Why does this not work? Because I lost the word open prime sieve? No. Failed to synthesize prime gen type U, but it's right there. What did this say before? A type U. Now this is where it had this. Failed to synthesize prime gen. But you shouldn't have to synthesize it because it's right there. I need to give this a name. Does this need to be an explicit proof? No. I don't know why this is not allowed. You say prime sieve A. Now that works. Okay, that works. I don't get that. I don't understand why. I keep calling this A when it's alpha. Alpha is type U. The universe. X. We don't know what X is. So X is a alpha. Failed to synthesize prime gen A. Prime gen alpha. Because I'm outside of this. Is it because this is not actually there? Okay, so prime gen alpha. All I did was push this even further down. I am very confused here. Prime gen alpha. Okay, well, let's put type U back here. So it was going to be alpha is a type the universe. Gen A. Oh, sorry. This is where it needed. Yeah. Okay. So this, if I'm going to give it an argument, now I see. Except it didn't help. Is it because of this? And what's wrong with it? What is wrong with that? Function is expected. The term has type A. Alpha. It's because this word it's not an error with this. It's expecting a function because I passed it this as a parameter. This is what okay. I like it indented when it's like small like this to see what the scope of the. All it's doing is using these variables for all these definitions. Okay, but this now I'm going to go back to what I had before where I put this in every of these controls. Is this the same kind of thing? Maybe it is. Here. Function expected at prime sieve. Am I misspelling it? Is often due to meta variables. Yeah, so prime. I know I'm confident I can figure this out. I'm not entirely sure what I'm looking at. First of all, let's just get rid of all of this for now. Just in case something down here is throwing it off. I've had that happen before, many times. It's not that. Function expected. Now it's going to tell me it has type prop, right? It can be a prop if it just has all these. This is going to tell me it can't find prime gen A, right? Type class instance problem is stuck. I'm very, very confused here. Clearly. I expect this to work, right? But clearly it doesn't work, so Function expected. Prime sieve. Why? Again, how is prime gen different? Prime gen is a type U where class copy this exactly. I know I have something different here. Again, oh, these stupid friends. Okay. So we have to explicitly pass in. I've changed it several times, right? And then I keep changing it back. What is C? C? Ah. Oh. I was saying ah, but I don't. I have to restart the file because the import is. Oh, the blue tweak says I think it's because alpha is used as x colon alpha. You have alpha x as the variables in prime sieve. Okay. Got it. Alpha is used as x colon alpha. That's no longer happening. You have, sorry, I didn't see there. You have alpha x as the variables in prime sieve. These. Wait, I don't declare what x is here. That's, but why doesn't it complain here? Is there something in scope that says what does x, it think x is? X is some random type. Okay, so I need to say x alpha. Now, okay. Okay. Part of it is just practice. Learning what it's trying to tell you. Okay, so sometimes the syntax highlighting doesn't. I guess there's like two levels of syntax highlighting, and it messes up. So like one is what the editor does just on lexical analysis, and then the other one is like semantic highlighting, and that tends to lag behind. Like you can see, like these are comments that have weird highlighting. Okay. All right. So my goal is to prove that. So okay, if before I start trying to prove this, wasting time like I just did, maybe I should just validate this is actually something I want to prove. So we're saying C prime is just the C for, C composed with next. So if it's a sieve, then probably there's going to be some way to expose this set. Right? We're going to be able to obtain this set. Yeah, yeah. I'm not used to. So I want to. I think this is probably not important. We're going to say we're looking at the set of primes. So now this is. I still think this should work. It does work. Okay. Probably I can even say we need the parens. For all n, that's an element of Rx. N is greater than Cx. So, meaning N is greater than or equal to Cx, meaning that really we should do it right the other way. Cx is less or equal to N. Therefore, C is the minimum. And then C prime is greater than like less than is in lean is the fundamental thing, so I'm going to write it as less. C less than C prime. This is definitely what I want to prove. Oops. Kind of neat. You can't do that. I don't know why you can do that, but you can't do. You can do S prime without save. Apparently you can. Okay. Oh, I see what's happening. Maybe this is the. Yeah. See, it made up a thing called CX. C apostrophe X. So that's not allowed. Not good syntax. And it just kind of fails silently, thinking that you're introducing a variable you want to match on. You could say set option maybe auto explicit false. And oh, right. No, hang on. Because U is here. Right. Get rid of the U. Because I don't know what that's an implicit variable. I don't know what the right variable because that didn't make any difference. Red here. In U. And so now we're broken. I'd expect that to turn red. Thank you for the tip there. I think if I had seen it in time, I would have known what you were talking about. That's it. Okay, so I just didn't need that U there, and maybe someday when I need it, I'll learn why I need it. All right, so I do think this is something I want to prove. I want to say that right, that we're moving it, so we're capturing this as a prime. So we proved that it's a prime. This is it's the minimum of R, and that the new C is greater than C. Okay. As it stands, this is completely true of every prime. I mean, it's true of primes in general. Like for every prime, this is true. And because S and R and these are generated by these functions that depend only on the fact that they don't know anything about the state. They just know that it's a prime generator. So yes, of course, these functions are don't have anything to do with the prime sieve. And now we're making an assertion based on all these things that we hope to somehow prove from the internal state of the prime sieve. But so the thing that Rake offers that this doesn't offer is that is is that in the Rake map we have this bijection. So it's not we're not just talking about some set that exists mathematically like this. You give me a number C, and these sets exist. There are primes less than that number, unless it's 2. It might be the empty set, and then there are an infinite set of primes greater than that number. So they just always exist. These things are always, they don't depend on anything to do with your state. But this says, right, and so I was struggling to connect that to anything, and then I came up with this idea of a rake and a rake map. Okay, so now I have an object that can explicitly it provides a bijection. I can say that there is I can call this little method on the rake, or pass rake to this method or to this function, and if I find the right m, then it's equivalent to right. It's equivalent to these statements are equivalent that if the property holds for n, whatever property that I've associated with this rake map, in order to have an instance of this type, I have to prove that I can get the number. That if the property holds, if the property holds for a number n, I can get that number out of the rake somehow by passing in some other value. I can pass in this m and get this out. There's some m that exists, and because of that, I can enumerate every value that's in there. If I just pass in the entire set of natural numbers, I'll get 0 will map to something which will happen to be the minimal prime in the set, and then 1 will map to something, 2 will map to something, 3 will map to something. For anybody who didn't see this before, right, this is what I'm looking at. I'm taking the set of natural numbers greater than 2, and I'm like dividing them and moving them up. Like this split them into even and odds, and then got rid of the evens, because now we know it's a 2. Same thing for 3. That got rid of the multiples of 3, leaving the multiples of 5 and 7. And then 5, this leaves you like 8 little things with 7, 11, 13, these lines, right? That's the rake going down this line. Okay, bring that back to Earth. um, so yeah, right. So here, when I was writing all this, I was just trying to get at this idea that these sets exist, or that this is what a prime sieve does. Is it somehow inspects the set of the things that are not crossed out, and somehow obtains the minimum of that set that are, and then like R is defined as the function that is not uh, divisible by any of the primes in the set of S, which is all the primes less than C of X, than the current prime. And I think what this proof is trying to say, so the goal of this proof is that if I can prove these three things about a prime, about a thing that I'm calling a prime sieve, or maybe the idea is if it's a prime sieve, these three things ought to be obvious or possible to prove based on the state of the sieve, right? That's the idea. I'm guessing that. So I'm guessing that, and then I wanted to show that if I had those three statements, then I can show that, well, that I have a new so this is trivial, right? So this is why this line is trivial. So we implement that. We say apply and intro, and then we can just do dot here. Exact H2C. Why doesn't it see that? Unknown identifier H2C. It's right because I didn't say open prime sieve. Or we could say prime sieve H2C. And then we don't have to do that. Got it. Okay. So this is kind of redundant, that little part. But now I want to say, here's some garbage thing that Copilot's giving me. Probably will not even work, but see, yeah. So then we say nothing, a prime does not exist. So that I'm going to ignore this. Sometimes I just turn this off. I find Copilot extremely helpful for other languages, but not for, but then occasionally it gives me the full proof of something that I didn't even know I needed. Okay, so that's again, I don't want that. We'll try it. Case left. What's wrong with this? I have to. You need this to make it type check, and then it just shows you over here what goes in the blank. Okay, so case right by contra XP. So this is introducing all this hex P. Okay. The P exists. And I think I can say this. No, I cannot. Okay. All right, so by contra changes the goal from not exists to we have the hypothesis that it does exist, and we're going to show a contradiction. I don't remember why I was doing that, but that was the path I was going down, so let's find out. Why would that be the case? Just before I do this. So trying to prove that if a prime exists that is out of this range, why should that be a contradiction? I must have thought that was a contradiction at one point. Okay, so let me think. Okay, why do I think this is the case? Why do I think the entire thing is so I think that's the case because that's the definition of what it is, of what you find more primes. And the proof that you found the next prime without anything in the middle is that C was the minimum value of R. So assume that there was a prime in between C and R. So assume P and prime between C and C prime. So assume prime between prime P between C and show false. All right, so P is that prime and HP is the case. So now I should be able to show a contradiction somehow using these four facts. 3 facts, sorry. Probably 2 of them, right? So what's the argument? The argument is that yeah, sweetie, what's up? I'll be down in a little while, okay? I'm gonna wrap up in a bit. Not right now. I'll come down later. And C sharp and C prime. Sorry if I'm just yelling in everyone's ears there. Okay, but let me put into words what I think the argument is. Turn this off. It always distracts me when I write. So assume prime P between C and C prime. This cannot happen if n is true. This cannot happen. So show a contradiction. All right, so we can have this statement right here. So we say have. And the proof of that is exact prime. No, we say prime sieve dot h r min of x. That is that statement. I just took this line right here and moved it into the scope. So now we have word this here, and we're going to say let's call this hr min, right? All right. So we have a for all now. And so we're going to intro n. Why does that not work? Oh, because that's a, okay, hang on. I think I want to do cases on this, right? Cases, or by cases, hr min, or we say have, how do we do that? Cases hr, by cases. Cases hr. At hr? No. I thought you could do that. I thought you could make a. In fact, I did it over here. By cases, some proposition. Right? Why does that not work? What is the error? What is the error telling you? It's this again. That bothers me. Not this. Sorry. Still can't do that. So it has the type something that returns a prop, but it's expected to have a prop. Oh, this is the type. Okay, hang on a second. This is the type. I see what's happening now. How do I put it into words? This is true. This is true, and here's the proof. So it doesn't make sense to have multiple cases of this because there's only one case. The case is that it's true. Okay, so that's not what I wanted to do. I guess I was thinking that if that weren't true, well, if it weren't true, I would have a conflict with this, and that would be by contradiction. But if it is true, then I could do something. So, right. So let's go back to this contradiction here. So I still want to go by contradiction. Show a contradiction. I still want to bring HRmin into scope, but now what do I want to say? I think what I want to do is I want to say conv HRmin, H, I don't know why it's like it's HRmin, the min of R. What is it? Admit. Okay, that's not working. I don't know how to do this. So conv is a tactic that lets you. What I'm trying to do is I'm trying to get into this and do some manipulation on this. And there's some way to do that. And it's like I've never done it before, so I got to read the manual here. Conversion tactic mode. Inside a tactic lock, one can use the keyword conv to enter conversion mode. This mode allows you to travel inside assumptions and goals, even inside function abstractions and dependent arrows to apply rewriting or simplifying steps. Okay. And so let's follow along with this example and see what they're doing. Put it up here. So prior to this, up here, we have this goal, and it says conv. So we move from, we have the whole thing, we moved into the left-hand side. Completely discarding the right-hand side? Conv at A. Okay, I'm going to try that in a second. I guess that would make sense. Conv is a tactic, and then you say at the hypothesis you want. Yeah, that makes sense. But I don't know how to use conv either. This rewrites that. And I don't know how to use congruence either, but ABC, so A times B times C, and we're going to break it into A, B, and C. Case A and B and C, and then close out A by reflection. Okay, why? Or reflexivity, what is it called? Reflection. I have no idea what that just did. Left-hand side navigates to the left-hand side of the relation. There's also a right-hand side to navigate to the right-hand side. There are arguments to the current head function. Here the head function is multiplication. Right, so this is like the top of the AST. Hang on a second, they're calling me. Yeah, I've been at this a little long. I think it was 4 hours in my 3 hours almost, and then my camera stopped. All right, well, yeah, I'll just wrap this up. And then I've been going another 3 hours almost. So it's been just like 6. I don't know that I've done a lot of work on my thing here, but so let's try this. Conv at hrmin, and I'm not even sure this is the right tool for the job. Okay. That did move it into the, yeah. So it pushed like this goal onto the, right, the goal of proving false onto the stack, and now I'm proving this. And I say intro so intro n, and if I hit the backspace key, I'm back up here. Okay, so that didn't, like, I briefly introduced something, but it didn't, went away, right? So n is an element of R. So intro NLR. And then again, when I go back, nothing has changed. So I'd have to use this to, I see these are like local to the inside of here. I'm also just curious if I can do this. I don't think so. I don't think you can just, yeah, you have to, has to already exist. What about this? No, that wouldn't make sense. It's like, this is a tactic somebody wrote that extended the syntax that's already there. So you'd have to, like, you could make that happen, I think, but every author would have to do that. The author of con would have to do that. Right. So I don't even know. I'm just like pursuing what's here. So c of x is less than or equal to n. But there's n. We don't know what n is. N is an element of Rx. Yeah, okay. My brain is no longer functioning here. I learned a little bit about what com does. Now I can see how that works. I don't know that this is actually something I want to prove. I mean, I guess it is something I want to prove. I don't know that proving this is going to get me to the next step. So I'm just going to save my work here. I'm not going to check this in. Let's just see what I need to check in. Oh, I think I did make quite a few changes. So let's see how bad it is. Prime gen, this we define C prime, and then, all right, so I'll just call this cleanup for prime gen and prime sieve. Are these saved? No, they're not saved. So first they're going to be. You know, when I use version control, so it'd be, I kind of like it when everything just gets saved automatically. PyCharm does that. All right, so go to this, and I'm just going to check all this stuff in, and then I'm going to call it a night, at least for now. Yeah, see, I added these, and then I hadn't saved it, so now, because of that, like, at least when you go here, it ought to indicate that they're not saved or something. So I'm just going to say cleanup prime system. start on cleaning. Thank you for everybody who was watching this so far and wanted to watch it on YouTube later. This is at, the code right now is at github.com tangentstorm treesieve /treesieve, and sieve is spelled, I don't know if I'm going to keep it that name that, but that's what it is now. And maybe I'll remember to put a link in here, but I'll just paste it into the chat here. So in the chat, I just pasted a link to this thing. So it's the Zulip chat for Lean. Taking forever to load, but like it's this is where I've been. Maybe that's one of you. Somebody marked this, but I've been keeping notes on this thing for a while, and keeping kind of a devlog in this thread over here. And eventually, this is going to be a summer of code thing, and I will continue working on it and come back and. Yeah, just the general plan is I want to prove this thing in the middle here so that I can say, okay, these things suffice, and then I want to prove each one of these from the information in the rake sieve. But I guess that's going to have to wait for another day. And then even once I do that, I have to actually prove it like all the way down. But at least I have this. I have these two statements here that say these properties hold. So there's some bijection between these states and the internal state of it and the sets that I'm talking about, which should correspond very, very closely to the definition of R here, because if I go through each prime that I find and I remove it from the set of natural numbers, and I have I start greater than or equal to 2, so that I strip out the 1, those two things should produce exactly this set. Strip out multiples, that's rem, and then strip out greater than, or limit it to greater than or equal to 2, that's GTE. So these two operations should produce a data structure that has a bijection to this set, and then from there I can prove that I can obtain the I have to show that I actually get the minimum, but basically I should be able to show these things. So that's the idea. So if this proof gets me to prime gen, if this shows me that a prime sieve that is based on this is a prime gen, but I guess right. This is the if I prove that it is a working thing that generates a prime at each step and there's no primes in between, then this is the proof that it's a prime sieve, and then if that works, then I'll go through and try and complete these proofs. That's kind of the general plan. Anyway, I'm gonna go down and see what everyone else is doing downstairs, and appreciate everyone hanging out with me for the past 900 hours, and hopefully some of you thought to put it on twice X speed or something, or had something else to do while you were ramble. Anyway, appreciate it, and I will see you again soon.